At this precise moment, light that left a distant galaxy cluster 400 million years ago is finally reaching Earth. It has travelled across a void so vast that nothing exists within it. No stars, no planets, no atoms of hydrogen drifting in the darkness. For 400 million years this light crossed absolute emptiness, a region of space so thoroughly evacuated that it contains less matter per cubic light year than any laboratory vacuum humanity has ever created. And now, in this instant, that ancient light is striking the mirror of a telescope in New Mexico, adding one more data point to a map that reveals something no human being suspected until the late 20th century. The universe has a skeleton, not a metaphorical skeleton, not a poetic flourish, a literal structural architecture that organises all visible matter in the cosmos into a pattern so vast, so intricate, and so hauntingly familiar that when astronomers first glimpsed it, many reported the same involuntary reaction. They said it looked like looking at a slice of brain tissue under a microscope. They said it looked like the neural networks that give rise to consciousness itself. They said it looked impossibly like something alive. This structure has a name. It is called the cosmic web, and it represents the largest pattern that exists in the observable universe. The filaments of this web stretch across hundreds of millions of light years. The voids between them could swallow thousands of Milky Way galaxies. The nodes where the filaments intersect contain superclusters of galaxies so massive that they bend space-time itself into wells from which light struggles to escape. And until the Sloan Digital Sky Survey began systematically mapping millions of galaxies in 1998, humanity had no idea any of this existed. What you think you know about the universe, the spinning galaxies, the stellar nurseries, the collision of titanic clusters, represents a fraction of the story. Everything the channel has ever covered, every cosmic phenomenon that seemed to stretch the limits of comprehension, exists as a single thread in a tapestry so immense that comprehending its true scale requires abandoning every intuition you have ever developed about space and distance. If you want to see the universe as it actually looks, not as it appears in artists' renderings or simplified diagrams, but as the cold mathematics of observation reveals it to be, then please consider liking and subscribing. It genuinely helps more than you know. Are you ready? Let us begin at the only scale where human intuition still functions. Stand on Earth and look up at the night sky. On a clear night, far from city lights, you can see approximately 2,500 stars with the naked eye. Each of those stars belongs to the Milky Way galaxy, and every one of them lies within roughly 1,000 light-years of Earth, a distance that, while inconceivably vast by human standards, represents less than 1% of the Milky Way's total diameter. You cannot see the rest of the galaxy from where you stand. The 100 billion other stars, the ancient globular clusters orbiting in the halo, the supermassive black hole lurking at the galactic centre, 4 million times the mass of the Sun. All of this is invisible to the naked eye, hidden by dust, distance, and the limitations of human biology. But even if you could see the entire Milky Way spread before you in all its spiral glory, you would still be looking at something almost comically small compared to the structures that truly define the universe. The Milky Way is 100,000 light-years across. This number appears large until you place it in context. The Andromeda Galaxy, our nearest major galactic neighbour, lies 2.5 million light-years away, a distance 25 times the diameter of the galaxy itself. The journey from one galaxy to another requires crossing an abyss so empty that the intergalactic medium contains only a handful of atoms per cubic metre. Voyager 1, humanity's most distant spacecraft, travelling at its current speed of roughly 17 kilometres per second, would require over 17 billion years to reach Andromeda. The Sun will have long since expanded into a red giant, consumed the inner planets, and collapsed into a cooling white dwarf. Human civilization, and quite possibly humanity itself, will have ceased to exist in any recognisable form. And yet Andromeda is, cosmically speaking, so close to the Milky Way that the two galaxies are gravitationally bound to each other and will collide in approximately 4 billion years. This is the first lesson that must be internalised before the cosmic web can be understood. The distances between individual galaxies, distances so vast that crossing them lies beyond any technology, humanity will likely develop for centuries or millennia, represent the smallest scale of structure in the universe above the level of individual star systems. Galaxies are not randomly scattered through space like raindrops on a window pane. They cluster. They group together in patterns dictated by gravity and the initial conditions of the universe, patterns that become visible only when you zoom out far enough to see thousands of galaxies at once. The Milky Way belongs to a small gathering called the Local Group, which contains approximately 80 galaxies spread across roughly 10 million light-years. The Local Group, in turn, belongs to a larger structure called the Virgo supercluster, which contains approximately 100 galaxy groups and clusters spread across 110 million light-years. The Virgo supercluster is part of an even larger structure called Laniakea, a Hawaiian word meaning immense heaven, which spans 520 million light-years and contains roughly 100,000 galaxies. These numbers have already exceeded human intuition. 520 million light-years cannot be visualized. It cannot be compared to any distance within human experience. If you drove a car at highway speed without stopping, it would take you roughly 6 trillion years to cross Laniakea, more than 400 times the current age of the universe. The light now reaching Earth from the far edge of Laniakea began its journey when the first complex life was just beginning to emerge in Earth's oceans, when trilobites scuttled across the seafloor of a world that would not see dinosaurs for another 250 million years. And yet, here is the truth that transforms everything. Laniakea, this structure so vast that describing it requires abandoning all conventional language of distance, is not the largest structure in the universe. It is not even close to the largest structure in the universe. Laniakea is one filament. The cosmic web contains thousands of structures like Laniakea, and they are not scattered randomly through the void. They are connected to each other. They form strands and sheets and walls that wrap around unimaginably vast, empty regions, creating a foam-like architecture that repeats self-similarly across the entire observable universe. The filaments stretch for hundreds of millions of light-years. Some of them span 1 billion light-years or more. They contain most of the visible matter in the cosmos, while the voids between them contain almost nothing at all. This is the structure that no one knew existed until 1989. This is the structure that appears when you map not thousands of galaxies, not millions, but hundreds of millions. When you treat each galaxy not as an object of study, but as a single data point in a 3-dimensional survey so comprehensive that it reveals patterns invisible to any smaller observation. The discovery of the cosmic web rewrote cosmology. It answered questions that had puzzled astronomers for decades, and it raised new questions that remain unanswered today. Understanding how it was found requires understanding what astronomers were looking for in the first place, and why the universe's true appearance remained hidden for so long. For most of the 20th century, cosmologists assumed that the universe was roughly homogeneous on large scales. This assumption arose from a combination of observational limitations and theoretical elegance. Albert Einstein's general relativity, when applied to the universe as a whole, produced equations that were vastly simplified if you assumed that matter was distributed evenly throughout space. The cosmological principle, as this assumption came to be called, stated that the universe should look essentially the same in all directions and from all locations, at least when viewed on sufficiently large scales. Small-scale clumpiness was expected. Stars gather into galaxies, galaxies gather into clusters. But the conventional wisdom held that once you zoomed out far enough, these irregularities would average out into a smooth, uniform distribution. The cosmological principle was not chosen arbitrarily. It emerged from observations that, at the time, seemed to support it. The cosmic microwave background radiation, the afterglow of the Big Bang discovered in 1965, appeared almost perfectly uniform across the sky. The temperature of this ancient light varied by only a few parts in 100,000 from one direction to another. This near-perfect smoothness suggested that the early universe had been extraordinarily homogeneous, and if matter started out evenly distributed, it seemed reasonable to assume that it remained relatively even as the universe expanded. But there was a problem. The galaxies that astronomers could actually observe did not appear to be evenly distributed. They clumped together into clusters. The clusters appeared to group into superclusters, and some astronomers, working with limited data and primitive computers, began to suspect that the superclusters themselves might be arranged in patterns that would violate the cosmological principle if they existed on large enough scales. The first hints emerged in the 1970s. Astronomers, using early spectroscopic surveys to measure the distances to galaxies, began noticing something strange. The galaxies in certain regions of the sky all appeared to be at roughly the same distance from Earth, as if they were arranged on the surface of an invisible sphere. In other directions, galaxies were conspicuously absent, as if something had swept them away. The data was sparse and the uncertainties were large, but a few researchers began to suspect that they were seeing the edges of vast empty regions, bubbles in the cosmic distribution of matter. The breakthrough came in 1981, when three astronomers, Robert Kirshner, Augustus Umlaut Jr., Paul Schechter, and Stephen Scheckman, published a paper describing the largest empty region ever discovered. Working with data from a survey of just a few hundred galaxies, they identified a spherical void in the constellation Boötes that appeared to contain almost no galaxies at all. The void was approximately 300 million light-years in diameter. At the time, this discovery was met with skepticism. The sample size was small and the statistical significance was uncertain. Many astronomers suspected that the Boötes void was simply a statistical fluctuation, an artifact of incomplete data that would disappear when more galaxies were mapped. They were wrong. The Boötes void was real, and it was just the beginning. The evidence accumulated throughout the 1980s. In 1986, Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics completed the first systematic redshift survey of the nearby universe. Using a modest telescope and painstaking spectroscopic measurements of roughly 15,000 galaxies, they constructed a three-dimensional map of the cosmic neighborhood, extending out to about 600 million light-years. What they saw changed astronomy forever. The galaxies were not randomly distributed. They were not smoothly distributed. They were arranged in thin sheets and elongated filaments that surrounded enormous empty voids. The structure looked, Geller later said, like the inside of a soap bubble. The galaxies traced the surfaces where the bubbles met, leaving the interiors almost completely vacant. One particular feature in their map became iconic. They called it the Great Wall. It was a sheet of galaxies extending across 500 million light-years of space, containing thousands of individual galaxies arranged in a structure so thin relative to its length that it resembled a cosmic membrane. The Great Wall was the largest coherent structure ever discovered in the universe at that time, and its existence posed immediate problems for the standard cosmological models. If the universe was supposed to be homogeneous on large scales, why were there structures hundreds of millions of light-years across? The cosmological principle was not disproven. The Great Wall represented only a small fraction of the observable universe, and it was possible that the distribution would smooth out on even larger scales. But the principle was severely challenged. The universe, it seemed, had far more structure than anyone had anticipated. The discovery of the Great Wall launched a new era of observational cosmology. Astronomers realized that they needed much larger surveys, not thousands of galaxies, but hundreds of thousands or millions, to determine how far the structure extended, whether even larger features existed, and whether the universe eventually became homogeneous at some scale, or remained structured all the way out to the observable horizon. This realization led directly to the Sloan Digital Sky Survey, the most ambitious mapping project in the history of astronomy. The Sloan Digital Sky Survey began operations in 2000, using a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico. The telescope was equipped with a revolutionary imaging camera containing 30 charge-coupled devices capable of capturing images of a quarter of the entire sky in 5 different wavelengths of light. More importantly, the survey was designed from the ground up to measure the distances to galaxies automatically and efficiently, using fiber optic cables to capture the spectra of 640 galaxies simultaneously. To appreciate what this represented, consider the historical context. Margaret Geller and John Huchra's groundbreaking survey in the 1980s had required years of painstaking work to map 15,000 galaxies. The Sloan Digital Sky Survey would eventually map over 1 million galaxies in its first phase alone, and later phases would extend this to tens of millions. The increase in data volume was not incremental. It was transformative. enabling astronomers to see patterns that simply could not emerge from smaller samples. The early results from the Sloan survey confirmed everything that Geller and Huckra had discovered, while extending the picture to far greater distances and with far greater precision. The cosmic web was not a local phenomenon. It stretched across the entire volume that the survey could reach. Filaments hundreds of millions of light-years long connected massive galaxy clusters. Voids, hundreds of millions of light-years across, contained almost nothing but the faintest dwarf galaxies. The foam-like structure repeated with variations throughout the observable universe. But the Sloan survey revealed something else, something that transformed a merely remarkable discovery into one of the most profound insights in the history of cosmology. The structure was not random. It followed rules. The filaments had characteristic widths, and the voids had characteristic sizes, and these characteristics could only be predicted, by a specific set of physical processes occurring in the first few 100,000 years after the Big Bang. This was the moment when the cosmic web became not merely an observed phenomenon, but a probe of fundamental physics. The pattern visible in galaxy surveys conducted in the early 21st century contained information about events that occurred nearly 14 billion years ago. Reading that pattern correctly required understanding how tiny ripples in the primordial plasma of the early universe grew, over billions of years, into the largest structures that exist. The story of how this happened, how quantum fluctuations in the first instant after the Big Bang became filaments spanning hundreds of millions of light-years, is one of the most extraordinary examples of scientific prediction ever achieved. To tell it properly requires stepping back in time to the epoch when the universe was less than 400,000 years old, when no stars existed, when no galaxies existed, when the entire cosmos was filled with a fog of hot plasma so dense that light could not travel more than a short distance before being absorbed and re-emitted. In this primordial fog, sound waves travelled. Not sound as humans experience it. There was no air, no molecules in the conventional sense, but pressure waves in the plasma, regions of slightly higher density chasing regions of slightly lower density, at speeds approaching half the speed of light. These sound waves, called baryon acoustic oscillations, were imprinted on the plasma by quantum fluctuations that occurred during cosmic inflation, the theorized period of exponential expansion in the first fraction of a second after the Big Bang. When the universe was approximately 380,000 years old, it cooled enough for the electrons and protons in the plasma to combine into neutral hydrogen atoms. This event, called recombination, had a dramatic consequence. The plasma became transparent. Light that had been trapped in the fog was suddenly free to travel unimpeded across the cosmos. The sound waves, which had been propagating through the plasma, were frozen in place. The universe fell silent, but the pattern remained. Where the sound waves had compressed the plasma, matter was slightly denser. Where they had rarefied it, matter was slightly less dense. These density variations were tiny, on the order of 1 part in 100,000, but they were enough. Gravity, patient and relentless, began its work. Over millions of years, the denser regions attracted more matter, becoming denser still. The less dense regions lost matter, becoming emptier. The tiny ripples amplified into waves, the waves into swells, the swells into the cosmic tsunami that would eventually produce every galaxy, every star, every planet in the universe. The pattern of the sound waves determined the pattern of the structure. The distance that sound could travel in the 380,000 years before recombination, a distance corresponding to about 490 million light-years in today's expanded universe, became imprinted on the cosmic web as a characteristic scale. Galaxy pairs are slightly more likely to be separated by this distance than by slightly larger or smaller distances. The filaments and voids of the cosmic web carry the echo of these ancient sound waves, frozen in space, stretched by cosmic expansion, but still detectable to surveys precise enough to measure them. When the Sloan Digital Sky Survey measured the characteristic separation of galaxies and found that it matched the theoretical predictions of baryon acoustic oscillations, it provided one of the most powerful confirmations of the standard cosmological model ever achieved. The cosmic web was not just a structure, it was a fossil. It preserved information about the first moments of cosmic history in a form that could be read 14 billion years later by observers patient enough to map millions of galaxies. This fossil told a consistent story. The The universe began in a state of near-perfect uniformity, with tiny quantum fluctuations seeding the initial density variations. Those variations grew under gravity's influence, attracting dark matter into halos that formed the scaffolding for the cosmic web. Ordinary matter, the protons and neutrons that would eventually form stars and planets and people, followed the dark matter, falling into the gravitational wells and accumulating in the filaments, while the voids emptied themselves into the surrounding structure. The process is ongoing. The cosmic web is not static. It continues to evolve today, with matter flowing along the filaments toward the nodes where galaxy clusters grow ever more massive. In the voids, the expansion of the universe dominates over gravity's pull, and these empty regions grow emptier still. Over billions of years, the contrast between the dense filaments and the vacant voids has sharpened, producing the foam-like structure visible in modern surveys. To see this structure directly, to perceive the cosmic web not as a diagram or simulation, but as an observed reality, requires visualizing the data from surveys like SDSS in 3 dimensions. When this is done, when millions of galaxy positions are plotted in their correct spatial locations and viewed from a virtual camera that can zoom in and out across billions of light years, the effect is genuinely uncanny. The first thing that strikes viewers is the apparent organization. The galaxies do not scatter randomly. They arrange themselves into threads and sheets that weave through space with an almost organic quality. The filaments branch and connect like the strands of a spider's web or the hyphae of a vast cosmic fungus. The voids between them are not perfectly spherical, but take on irregular, bubble-like shapes, with thin walls of galaxies separating one void from the next. The second thing that strikes viewers is the scale. A single pixel in these visualizations may represent a volume containing thousands of galaxies. A filament that appears delicate and thread-like spans distances larger than anything the human mind can genuinely comprehend. The viewer is not looking at objects in any conventional sense. They are looking at statistical patterns, probability densities made visible, the fingerprints of physical law written across a canvas so immense that traversing it at the speed of light would require billions of years. The third thing that strikes viewers, and this is the observation that has captured popular imagination more than any other, is the resemblance to biological structures. The cosmic web looks like a brain. More precisely, it looks like a microscope image of neural tissue, with the filaments resembling the axons that connect neurons, and the nodes resembling the cell bodies where neural connections cluster. This resemblance is not coincidence, but it is also not evidence of any mystical connection between the cosmos and consciousness. Both the cosmic web and the neural networks of the brain are shaped by similar mathematical principles. Both are networks that optimize for connectivity while minimizing resource usage. Both emerge from processes where local rules, gravity in one case, chemical signaling in the other, produce global structure through repeated iteration. The cosmos is not conscious, and the brain is not a miniature universe. But both are examples of how simple physical processes, operating across vast scales of space and time, can produce patterns of stunning complexity. The resemblance has been quantified. In 2020, an astrophysicist and a neuroscientist published a detailed comparison of the cosmic web and the neural networks of the human brain. They analysed the number of nodes, the typical length of connecting filaments, the clustering of connections, and several other network properties. Their conclusion was striking. The two networks were more similar to each other than either was to other complex networks like social networks or the internet. The cosmic web and the human brain occupy a similar region of the mathematical space of possible network structures. This finding does not elevate either structure to a special status. It demonstrates instead how universal certain mathematical patterns are. The same optimization principles that shape neural networks in the brain also shape the distribution of matter in the cosmos. This is not because the universe is thinking or because consciousness pervades creation. It is because mathematics itself constrains the forms that complexity can take, regardless of the physical substrate. But the emotional impact of the resemblance is undeniable. When humans look at the cosmic web, they see something that echoes the architecture of thought itself. The largest structure in existence mirrors the structure that allows existence to be contemplated. Whether this is meaningful or merely coincidental remains perhaps a question for philosophers rather than physicists. The physical reality of the cosmic web does not depend on its resemblance to anything familiar. The filaments exist whether or not they remind viewers of neurons. The voids persist whether or not they evoke the spaces between thoughts. What matters to cosmology is not how the structure appears, but what it reveals about the universe's history, composition, and fate. And what it reveals is extraordinary. The pattern of the cosmic web encodes the ratio of ordinary matter to dark matter in the universe. It encodes the rate at which the universe expanded in its first moments. It encodes the properties of dark energy, the mysterious force driving the accelerating expansion of the cosmos. Every filament, every void, every node in the network carries information about fundamental physics, written in a language that required decades to learn to read. The reading is still ongoing. New surveys are mapping ever larger volumes of the universe with ever greater precision. The Dark Energy Spectroscopic Instrument, which began observations in 2021, will measure the redshifts of 40 million galaxies, extending the map of the cosmic web to distances and depths never before achieved. The Euclid Space Telescope, launched in 2023, is imaging billions of galaxies to trace the evolution of cosmic structure over the past 10 billion years. The Vera C. Rubin Observatory, under construction in Chile, will survey the entire visible sky repeatedly for a decade, creating a movie of the universe that will reveal structures too subtle to appear in any single snapshot. These instruments will test our understanding of dark matter, dark energy, and gravity itself. They will measure whether the cosmic web grows in the way our theories predict or whether deviations reveal new physics, lurking beneath the surface of the standard model. They may discover structures even larger than anything yet observed, patterns that emerge only when billions rather than millions of galaxies are mapped. But even with the data we possess today, the cosmic web has already transformed humanity's understanding of its place in the universe. We live not in a smooth, featureless void dotted with occasional stars, but within a specific address in a cosmic architecture that spans the observable universe. The Milky Way occupies a position within the local sheet, a small structure within the local cosmic web. The local sheet connects to the Virgo supercluster filament, which in turn connects to the larger structure of Laniakea. Laniakea is one node in a network of superclusters that extends to the limits of observation, and, almost certainly, far beyond. Where exactly does Earth sit within this vast structure? The Milky Way lies near the edge of the local void, one of the nearer large voids identified by astronomers. Our galaxy is not at the centre of any significant structure. It is not at a particularly privileged location. It exists, as Earth exists within the solar system, and the solar system exists within the galaxy, at an unremarkable position that happens to be the one from which we observe everything else. This unremarkable position has a name in cosmology. It is called the Copernican principle, the idea that there is nothing special about our location in the universe. Copernicus dethroned Earth from the centre of the solar system. Later astronomers dethroned the solar system from the centre of the galaxy, and the galaxy from the centre of the universe. The cosmic web completes this dethroning. We are not at the centre of any filament, any supercluster, any grand cosmic structure. We are simply here, in one thread of a web so vast that our position within it conveys no special significance whatsoever. And yet, and this is the paradox that makes cosmology such a peculiar science, the universe appears essentially the same from every position within it. This is the cosmological principle reasserting itself, not as a claim about local structure, but as a claim about statistical averages. Any observer, anywhere in the observable universe, would see approximately the same cosmic web extending in all directions. The patterns would differ in detail, but the statistical properties, the typical filament lengths, the typical void sizes, the characteristic scale imprinted by baryon acoustic oscillations, would be identical within measurement uncertainties. This homogeneity is itself profound. It implies that the physical laws governing the universe are the same everywhere, that the initial conditions of the Big Bang were the same everywhere, that the processes shaping cosmic structure operated consistently across all of space and all of time. The cosmic web is not a local peculiarity. It is universal, and its universality makes it a probe of physics far more reliable than any laboratory experiment could ever be. The filaments, now stretching across hundreds of millions of light years, began as quantum fluctuations smaller than an atom. The voids, now spanning distances that light requires hundreds of millions of years to cross, began as infinitesimally small underdensities in the primordial plasma, The entire structure that we now map with dedicated telescopes and billion-dollar instruments was, in the first instant after the Big Bang, compressed into a region smaller than a proton. This is the scale of the story that the cosmic web tells. It is a story that connects the smallest scales of quantum mechanics to the larger scales of cosmic structure. It is a story that spans 14 billion years and trillions of light years. It is a story written in the positions of galaxies, in the emptiness of voids, in the clustering of matter along invisible threads of dark matter that humanity cannot see directly, but can infer from the structure of everything visible. The darkness between the filaments is not merely empty space. It is a record of cosmic history, a testament to the processes that gathered matter into the web while leaving the voids behind. Every void is a negative space that defines the positive structure around it. Every emptiness contributes to the pattern. The absence of galaxies in a void is as informative, cosmologically, as the presence of galaxies in a filament. This is the universe as it actually looks, when viewed at a scale large enough to perceive its true architecture. Not a random scattering of points, not a smooth, featureless expanse, a web, a foam, a structure of stunning complexity and haunting familiarity, stretching across distances that dwarf everything the human mind has ever tried to comprehend. The question that remains, the question that the next generations of surveys will attempt to answer, is how far this structure extends. The observable universe is not the entire universe. It is merely the region from which light has had time to reach Earth since the Big Bang. Beyond the observable horizon, more universe exists, perhaps infinitely more. Does the cosmic web continue, with the same statistical properties, into the unobservable regions? Do the filaments and voids stretch forever, repeating their patterns across infinite space? Or does the structure eventually give way to something else? Some pattern we cannot imagine because we cannot observe the regions where it would appear. These questions cannot currently be answered. They may never be answerable because the light from those regions will never reach us. But the questions matter nonetheless, because they concern the nature of the universe itself, not merely the part we can see, but the whole of which our observations reveal only a fraction. What we can say, with the confidence that comes from 2 decades of precision cosmology, is that the cosmic web visible from Earth is not a local phenomenon. It extends to the limits of observation. The largest structures we can see are filaments and voids approaching 1 billion light-years in extent, and these structures show no sign of being the largest that exist. The pattern continues consistent and self-similar, as far as our telescopes can reach. And this brings us to the edge of something unsettling. The cosmic web is not infinite in extent within the observable universe. It has structure at the larger scales, but at some point it must give way to homogeneity. Otherwise the cosmological principle would be violated, and our models of cosmic evolution would fail to match the uniformity of the cosmic microwave background. The scale at which homogeneity is reached has been estimated at roughly 300 to 400 megaparsecs, about 1 billion to 1.3 billion light-years. Beyond this scale, the universe does, in some statistical sense, become smooth. But smooth is a relative term. A billion light-years is still a distance that contains vast amounts of structure. The transition from web to homogeneity is not sharp but gradual, and the structures visible at scales just below the homogeneity threshold are among the most impressive phenomena that cosmology has revealed. There is the Sloan Great Wall, discovered in 2003, stretching 1.37 billion light-years across the northern sky, the largest known structure at the time of its discovery. There is the Hercules Corona Borealis Great Wall, announced in 2013, extending across roughly 10 billion light-years according to some estimates, though its reality and extent remain controversial. There are the cold spots and hot spots in the cosmic microwave background that suggest even larger structures, possibly primordial in origin, imprinted on the universe in its first moments. Each of these discoveries pushes against the limits of what our models can accommodate. Each raises questions about whether the cosmic web is merely one layer of structure in a hierarchy that extends to ever larger scales, or whether it truly represents the largest level of organization in the cosmos. The answers lie in data not yet collected, in observations not yet made, in telescopes not yet built. But the questions themselves have transformed how humanity thinks about the universe. We no longer imagine a cosmos of scattered points. We imagine a web, We imagine structure where we once imagined void. We imagine pattern where we once imagined randomness. And we imagine, perhaps for the first time, that the universe at its largest scales resembles not a machine or a void or a chaos, but something that echoes the structure of thought itself, a web that connects all things, an architecture that spans all distances, a pattern that emerges from the simplest initial conditions and grows over billions of years into something that looks, impossibly and hauntingly, like it was designed to be seen. But here lies the cruel paradox that makes the cosmic web so difficult to truly comprehend. We have described its scale in numbers. We have invoked light years and megaparsecs. We have spoken of structures spanning billions of years of light travel time. And yet these descriptions, precise as they are, fail to convey what it would actually mean to experience the cosmic web, to see it not as a diagram in a journal or a simulation on a screen, but as a physical reality through which one might travel. Consider what it would mean to journey across a single filament. You begin at one galaxy cluster, a collection of perhaps 1,000 galaxies bound together by gravity, spanning roughly 10 million light-years in diameter. This cluster is your starting point, your port of departure. You will cross the filament to reach the cluster on the other side, another gravitationally bound collection of galaxies, another island of concentrated matter in the cosmic ocean. The distance between these two clusters, along the axis of the filament, is approximately 300 million light-years. 300 million light-years. The phrase rolls off the tongue with an ease that conceals its meaning. Let us make it concrete. At the speed of light, the absolute maximum velocity permitted by the laws of physics, the speed at which massless particles traverse the vacuum, your journey would require 300 million years. When you departed, the dinosaurs would not yet have evolved. Earth would be in the midst of the Carboniferous period, dominated by vast swamps and primitive insects. By the time you arrived, every species that existed at your departure would be extinct. Every mountain would have eroded. Every continent would have shifted. Human beings would have evolved, built civilizations, destroyed civilizations, built new ones, and quite possibly gone extinct themselves, all during your crossing of a single filament. But you cannot travel at the speed of light. No massive object can. The fastest spacecraft humanity has ever built, the Parker Solar Probe, travels at approximately 430,000 miles per hour relative to the Sun. At this velocity, which represents the absolute pinnacle of human engineering, achieved through gravitational assists and decades of technological development, your journey across the filament would require not 300 million years, but approximately 470 billion years. This is more than 30 times the current age of the universe. The stars themselves would have burned out before you completed your crossing. The galaxies would have exhausted their hydrogen fuel. The universe would have entered its degenerate era, populated only by stellar remnants and slowly evaporating black holes. And still you would not have reached the other side of a single filament. This is not an argument against space travel. It is a statement about scale. The cosmic web exists at dimensions so far beyond human experience that our most ambitious achievements, our fastest spacecraft, our most powerful rockets, our dreams of interstellar travel, register as essentially zero on the scale of filamentary structure. We have discussed, in previous explorations, how time dilation might theoretically allow a human to cross distances that would otherwise require generations. But even relativistic travel, even the bending of time itself, cannot compress the cosmic web into anything resembling human accessibility. A traveller accelerating at 1g for a year, then decelerating for a year, could reach the nearest stars. The same traveller, maintaining the same acceleration profile, would require approximately 20 years of ship time to cross 300 million light-years. But those 20 years of ship time would correspond to 300 million years passing on Earth. The traveller would arrive in a universe utterly transformed, in a cosmos where Earth itself might no longer exist, where the sun had long since exhausted its fuel and swelled into a red giant, where every memory of human civilization had been erased by time. The cosmic web is not merely large, it is inaccessible in a way that defies the very concept of journey. It can only be observed, never visited. It can only be mapped, never explored. It exists on scales that reduce even our most grandiose dreams of cosmic expansion to exercises in local motion, shuffling between nearby stars while the vast architecture of the universe remains forever out of reach. And yet, we see it. That is the remarkable thing. We cannot go there, but we can look. We cannot traverse it, but we can map it. And the maps we have built, through the labour of thousands of astronomers over decades of observation, reveal a structure so intricate, so unexpectedly organised, that it challenges our basic assumptions about what the universe should look like. The first comprehensive maps of the cosmic web emerged from the CFA Redshift Survey, conducted at the Harvard-Smithsonian Center for Astrophysics between 1977 and 1982. Margaret Geller and John Huchra led this effort, measuring the redshifts of approximately 2,400 galaxies in a narrow slice of the northern sky. The results, published in 1986, shocked the astronomical community. Instead of the uniform distribution predicted by simple cosmological models, Geller and Huchra found structure. Galaxies clustered along sheets and filaments. Vast regions of space appeared nearly empty. The pattern resembled, in Geller's memorable description, soap bubbles, thin walls of matter surrounding enormous voids. The most striking feature of these early maps was the Great Wall, a filamentary structure stretching across 500 million light-years of space, the largest coherent structure ever observed at that time. The Great Wall was not a single object in the sense that a galaxy is an object. It was a pattern, a tendency, a concentration of matter along a sheet-like region of space that connected multiple galaxy clusters into a single recognizable form. Its existence demonstrated that the universe possessed structure at scales far larger than anyone had anticipated. But the CFA survey covered only a small fraction of the sky. Its sample of 2,400 galaxies represented a sparse sampling of cosmic structure. The true complexity of the cosmic web would require surveys of unprecedented ambition, surveys that could map not thousands but millions of galaxies, that could cover not narrow slices but substantial fractions of the entire celestial sphere. This ambition would be realised over the following decades by the Sloan Digital Sky Survey. SDSS began operations in the year 2000, using a dedicated 2.5-metre telescope at Apache Point Observatory in New Mexico. The telescope was designed from the outset for survey work, equipped with a camera containing 30 charge-coupled devices arranged in 6 columns, capable of imaging a swath of sky roughly 3 degrees wide. This camera would eventually capture images of approximately 1/3 of the entire celestial sphere, more than 500 million unique objects, including stars, galaxies, and quasars, each precisely positioned and characterized. But imaging was only the first step. To map the cosmic web, astronomers needed distances. The angular positions of galaxies tell you where they appear on the sky, but not how far away they are. Without distances, a 3-dimensional map is impossible. You have only a projection, a flattened image that cannot distinguish between a nearby dwarf galaxy and a distant giant, between a local void and a faraway supercluster. The solution was spectroscopy, the same technique that had revealed the expansion of the universe in Hubble's hands nearly a century earlier. Each galaxy's spectrum carries the signature of its recession velocity, encoded in the redshift of its spectral lines. By measuring redshifts for vast numbers of galaxies, SDSS could convert angular positions into 3-dimensional coordinates, building a map of cosmic structure that showed not just the sky, but the actual spatial distribution of matter throughout a significant volume of the universe. The scale of this undertaking defies easy description. SDSS obtained spectra for more than 4 million objects across its various phases, including over 2 million galaxies and more than 500,000 quasars. Each spectrum required the careful positioning of an optical fibre on a metal plate, drilled to match the precise coordinates of target objects. Hundreds of thousands of these plates were manufactured over the survey's lifetime, each one a physical artifact of humanity's determination to map the cosmos. The fibres fed starlight into a spectrograph, which dispersed it into its component wavelengths and recorded the pattern on a detector. The recorded patterns were then analysed by automated software, extracting redshifts and other physical properties from the faint traces of light. The result was a revolution in cosmological cartography. For the first time, humanity possessed a 3-dimensional map of the universe extending across billions of light-years, populated by millions of precisely positioned galaxies. And this map revealed the cosmic web in unprecedented detail. The structure visible in SDSS data is fractal in character. meaning that it displays similar patterns at multiple scales. Zoom out, and the web of filaments and voids remains recognizable. Zoom in, and smaller filaments and smaller voids appear within the larger structures. This self-similarity extends across roughly 3 orders of magnitude in scale, from structures a few million light-years across to structures approaching 1 billion light-years. Beyond this range, the self-similarity breaks down. At the smallest scales, individual galaxies dominate the pattern, and at the largest scales, the homogeneity of the universe asserts itself, smoothing out the web into statistical uniformity. But within the fractal regime, the patterns are extraordinary. SDSS revealed not just individual filaments, but vast networks of interconnected filaments, spanning the entire survey volume. It revealed voids nested within voids, smaller empty regions embedded within larger ones. It revealed the nodes where filaments intersect, marked by the massive galaxy clusters that form at these cosmic crossroads. And it revealed the walls, the sheet-like structures where filaments merge, creating planar concentrations of matter that stretch across hundreds of millions of light-years. The Sloan Great Wall, discovered in SDSS data in 2003, exemplifies these structures. Stretching 1.37 billion light-years across the northern sky, it represents the largest known coherent structure in the local universe. Its existence was not predicted by simple cosmological models. Its scale approaches the threshold of homogeneity, the point at which structure should give way to uniformity. And yet there it is, a genuine feature of cosmic architecture, visible in the data, confirmed by follow-up observations, as real as the galaxies that compose it. But SDSS was only the beginning. Subsequent surveys have pushed even deeper into the cosmos, mapping structure at ever greater distances and ever finer resolution. The 2DF Galaxy Redshift Survey, conducted at the Anglo-Australian Observatory, obtained spectra for more than 220,000 galaxies, providing an independent confirmation of the web-like structure revealed by SDSS. The 6DF Galaxy Survey extended this work to the southern hemisphere, mapping more than 125,000 galaxies. The Wigglesy Dark Energy Survey targeted blue star-forming galaxies at higher redshifts, probing the cosmic web at earlier epochs when the universe was younger and smaller. Each survey added detail to the emerging picture. Each confirmed the basic architecture: filaments, voids, walls, clusters, while revealing new subtleties and complexities. The cosmic web was not a static structure, but a dynamic one, evolving over billions of years as matter flowed along filaments and accumulated at nodes. The surveys captured snapshots of this evolution, showing how the web appeared at different cosmic epochs, how it had grown and changed as the universe aged. The most recent generation of surveys has achieved a precision that earlier astronomers could scarcely have imagined. The Dark Energy Spectroscopic Instrument, or DISI, began operations in 2021 at the Mail Telescope in Arizona. Its design represents a quantum leap in survey capability: 5,000 robotic fiber positioners, each capable of independently targeting a galaxy or quasar, each repositioning itself in minutes to observe a new field. In its first year of operations, DESI obtained more spectra than SDSS gathered in its entire 2-decade existence. By the time its survey is complete, DESI will have measured redshifts for approximately 40 million galaxies and quasars, creating a map of the cosmic web 10 times larger than any that came before. The preliminary results from DESI, released in 2024, have already begun to reshape our understanding of cosmic structure. The web appears in these new maps with unprecedented clarity, not as a schematic or a cartoon, but as a genuine 3-dimensional reality, dense with detail, rich with pattern, extending across the full depth of the observable universe. For the first time, we can see filaments not as statistical abstractions, but as physical features, tracing their paths across billions of light-years, watching them connect cluster to cluster in vast bridges of dark matter and gas. And this brings us to the essential question that the subtitle of this exploration promised to address. What does the cosmic web actually look like? The answer depends on what you mean by look. The cosmic web is not directly visible to human eyes, even with the most powerful telescopes. What we observe are galaxies, points of light scattered across the sky. The web itself consists largely of dark matter, which emits no light and interacts with ordinary matter only through gravity. The filaments are traced by galaxies, much as a string of streetlights might trace a highway at night, but the underlying structure, the gravitational scaffolding that organises those galaxies, remains invisible. To truly see the cosmic web, we must construct visualizations from data. We must take the positions of millions of galaxies and render them in 3 dimensions. We must smooth the data to reveal the underlying density field. We must color-code the structures to distinguish filaments from voids, nodes from walls. The resulting images are not photographs in the conventional sense. They are reconstructions, interpretations, translations of data into visual form, but they are not arbitrary. The patterns they reveal are real. The filaments exist. The voids are empty. The clusters mark genuine concentrations of matter. The visualizations may be false color and computer-generated, but they represent something physically present in the universe, something that would be there whether or not any observer existed to perceive it. And when you see these visualizations, when you encounter, for the first time, a rendering of the cosmic web as revealed by SDSS or DESI or one of the many other surveys, the effect is visceral. The structure does not resemble what most people expect the universe to look like. It does not resemble a uniform scattering of stars. It does not resemble the elegant spiral galaxies that adorn astronomical calendars. It does not resemble the familiar images of nebulae and planets that populate our collective imagination of space. It resembles something else entirely. It resembles a neural network. This is not a metaphor carelessly chosen. The comparison between the cosmic web and the structure of the brain has been made by serious scientists in peer-reviewed publications. In 2020, Franco Vazza of the University of Bologna and Alberto Folletti of the University of Verona published a paper in the journal Frontiers in Physics that quantified the structural similarities between the cosmic web and the neuronal network of the human brain. Their analysis compared the distribution of matter in cosmological simulations with the distribution of neurons in brain tissue samples, examining features such as spectral density, the distribution of connections, and the organization of nodes within networks. The results were striking. Despite a difference in scale of approximately 27 orders of magnitude, the cosmic web spans hundreds of millions of light-years, while the brain spans mere centimeters. The two systems exhibited comparable levels of complexity. Both contained approximately the same number of nodes, roughly 100 billion neurons in the human brain, roughly 100 billion galaxies in the observable universe. Both displayed similar distributions of connectivity, with some nodes highly connected and others sparsely linked. Both showed self-similar structure across multiple scales, with smaller networks nested within larger ones in fractal-like patterns. The comparison should not be pushed too far. The cosmic web and the brain are organized by entirely different physical processes, gravity and dark matter on one hand, biochemistry and evolution on the other. The similarities are structural, not functional. No serious scientist suggests that the universe is thinking, or that the brain has cosmological significance. But the visual resemblance is nevertheless arresting. It suggests that certain patterns of organization recur across vastly different systems, that complex networks tend towards similar architectures regardless of their underlying substrate. The comparison has captured the public imagination in ways that more technical descriptions of the cosmic web have not. When people see images of the cosmic web alongside images of neural tissue, they experience recognition. The structures look alike, the patterns echo, and this recognition transforms the cosmic web from an abstract concept into something almost familiar. Strange, yes, and impossibly vast, but not entirely alien. Other comparisons have been offered. Some observers see in the cosmic web the structure of a sponge, with matter concentrated along the surfaces of voids rather than uniformly distributed. Others see the branching patterns of rivers and tributaries, with matter flowing along preferred paths towards central confluences. Still others see the architecture of a city, with dense clusters connected by transportation corridors across empty suburbs. Each of these comparisons captures some aspect of the web's structure, and each falls short of conveying the full complexity of what the surveys have revealed. Perhaps the most accurate comparison is the one that gives this exploration its organizing image. Silk. The cosmic web resembles nothing so much as the finest silk fabric, woven at scales that exceed comprehension, translucent and delicate yet structurally coherent, draped across the void in patterns that seem almost intentional. This is what the cosmic web actually looks like, not points of light, Not empty darkness, not random scatter, but pattern, structure, architecture, a web that spans the cosmos, that connects all visible matter, that emerged from the quantum fluctuations of the early universe and grew over billions of years into the largest organized structure that exists. And we are within it, not observing from outside, not floating in some privileged vantage point, but embedded. The Milky Way is a node in this web. The Virgo supercluster is a junction where filaments meet. The Laniakea supercluster, of which Virgo is a part, is a region of gravitational influence within the larger cosmic flow. When you look at a visualization of the cosmic web, you're looking at your own address, the structure that contains you, the architecture that defines your cosmic neighborhood, the pattern of which you are an infinitesimal part. This realization transforms the meaning of the cosmic web from an astronomical curiosity into something more personal. We are not merely observers of the web, we are participants in it. We are made of matter that once flowed along its filaments, that accumulated at its nodes, that condensed into stars and planets, and eventually into beings capable of mapping the very structure that produced them. The cosmic web is not out there, separate and distant. It is here, woven into the fabric of existence, visible in the distribution of galaxies but present in every atom of our bodies. The question that naturally follows from this realization is one that has occupied cosmologists for decades. How did this structure come to be? The cosmic web did not appear fully formed. It grew, it evolved. It emerged from conditions so different from the present that the process of its formation constitutes one of the most remarkable transformations in the history of existence. To understand this transformation, we must travel backward through time, not merely millions or billions of years, but to the very beginning, to the first moments after the Big Bang, when the universe was a seething cauldron of energy so hot and so dense that matter as we know it could not exist. In those first fractions of a second, the temperatures exceeded trillions of degrees. The fundamental forces of nature were unified, then separated. Space itself expanded at velocities that exceeded the speed of light, not because anything moved through space that fast, but because space itself was stretching, carrying everything with it in a cosmic inflation that doubled the size of the universe again and again in inconceivably brief intervals. During this inflation, something crucial happened. Quantum fluctuations, the random, irreducible jitter that exists at the smallest scales of reality, became frozen into the fabric of the expanding universe. These fluctuations were tiny, representing variations in density of perhaps 1 part in 100,000. In any region of the early universe you would find the density to be almost perfectly uniform, with only the slightest deviations from place to place. But those slight deviations were enough. They would become the seeds of everything. When inflation ended, the universe continued expanding, but more slowly. It was still extraordinarily hot, filled with a plasma of electrons, protons, and photons so densely packed that light could not travel more than a short distance before scattering off a charged particle. The universe was opaque, like the interior of a star, glowing with energy but revealing nothing of its structure to any hypothetical observer. For approximately 380,000 years, this state persisted. The universe expanded and cooled, but remained a plasma, and the frozen quantum fluctuations remained hidden within it, density variations too small to see but crucial for everything that would follow. Then, as the temperature dropped below approximately 3,000 degrees Kelvin, something transformative occurred. Electrons, which had been moving too fast to be captured by atomic nuclei, slowed enough to combine with protons and form neutral hydrogen atoms. The process is called recombination, though it is poorly named since the electrons and protons had never been combined before. In a cosmic instant, a period lasting perhaps 100,000 years, which is an instant on cosmic timescales, the universe transitioned from plasma to gas. This transition had immediate and profound consequences. Light, which had been perpetually scattered by free electrons, could now travel freely. The universe became transparent. Photons that had been trapped in the plasma were released, streaming outward in all directions, carrying with them information about the conditions at the moment of release. These photons are still travelling today. They have been redshifted by the expansion of the universe from visible light to microwave radiation, and they now form the cosmic microwave background that scientists first detected in 1965 and have been studying with increasing precision ever since. The cosmic microwave background is not merely a relic of the early universe, it is a photograph of the cosmic web in its infancy. When scientists map the tiny variations in the temperature of this radiation, variations of a few hundred thousandths of a degree, they are seeing the density fluctuations that would eventually grow into the filaments, clusters, and voids we observe today. The slightly denser regions in the cosmic microwave background mark the locations where matter would accumulate. The slightly less dense regions mark the locations that would become voids. The pattern was already present, encoded in the radiation, waiting to be amplified by gravity over billions of years. After recombination, the universe entered what cosmologists call the Dark Ages, a period lasting several 100 million years during which no stars had yet formed, and the only light was the fading glow of the cosmic microwave background, red shifting toward invisibility as the universe expanded. During this time, the density fluctuations began their work. Regions slightly denser than average exerted slightly more gravitational attraction on surrounding matter. This attraction drew matter inward, increasing the density further, which increased the gravitational pull, which drew in more matter still. The process was slow at first, almost imperceptibly slow, but it was inexorable. Meanwhile, something else was happening, something that would prove even more important than the behaviour of ordinary matter. Dark matter, which outweighed ordinary matter by roughly 5 to 1, was undergoing the same gravitational collapse, but without the complications introduced by electromagnetic interactions. Dark matter does not interact with light, it does not experience pressure, it does not collide with itself or with ordinary matter in any way that we can detect except gravitationally. This apparent limitation is actually an advantage when it comes to structure formation. Ordinary matter, when it collapses, heats up. The compression generates pressure that resists further collapse. Dark matter experiences no such resistance. It falls inward freely, responding only to gravity, and this freedom allows it to collapse faster and more efficiently than ordinary matter can. The result is that dark matter led the way. It was dark matter that first accumulated into the dense regions marked by the primordial fluctuations. It was dark matter that formed the first gravitational wells, the first nodes in what would become the cosmic web. Ordinary matter, still interacting with the radiation that filled the early universe, followed more slowly, falling into the gravitational wells that dark matter had already carved out. This is why dark matter is so crucial to understanding the cosmic web. The web is, in its essence, a dark matter structure. The galaxies and gas that we observe are tracers, following the gravitational contours that dark matter defined. Remove the dark matter, and the cosmic web would not exist. The primordial fluctuations would have grown far too slowly to produce the structures we see today. The universe would be far more uniform, far less interesting, and almost certainly devoid of observers capable of contemplating it. Computer simulations have allowed scientists to model this process of structure formation in exquisite detail. The largest of these simulations, such as the Millennium simulation conducted in 2005 and its successors, track the evolution of billions of particles representing both dark matter and ordinary matter from the conditions present shortly after the Big Bang to the present day. The simulations begin with a nearly uniform distribution of matter, perturbed by the tiny density fluctuations measured in the cosmic microwave background. They then apply the known laws of physics, gravity, hydrodynamics, nuclear reactions, radiative cooling, and let the system evolve. What emerges is the cosmic web. The simulations show how the early fluctuations grow, how matter streams along the gradients of gravitational potential, how filaments form at the intersections of collapsing regions, how voids expand as matter drains away from them. The process is not instantaneous. It unfolds over billions of years, with different structures forming at different times. The first stars ignited approximately 100 to 200 million years after the Big Bang, ending the Dark Ages and beginning the cosmic dawn. The first galaxies assembled over the following hundreds of millions of years. The first clusters, collections of galaxies bound by gravity into single systems, formed within the first few billion years, and the filaments and voids, the larger structures, emerged gradually as the intermediate scales filled in the architecture between nodes. One of the most striking features of these simulations is their agreement with observations. When scientists compare the statistical properties of the simulated cosmic web with the actual distributions measured by surveys like the Sloan Digital Sky Survey, the match is remarkable. The distribution of galaxy separations, the sizes and shapes of voids, the connectivity of filaments, the masses of clusters, all of these properties in the simulations correspond closely to what the surveys reveal. This agreement is not merely satisfying. It represents a profound validation of our understanding of cosmology. It confirms that the basic framework, the Big Bang, inflation, dark matter, dark energy, general relativity, correctly describes the origin and evolution of cosmic structure. The cosmic web is not a mystery in the sense of being unexplained. We understand how it formed, we can simulate its formation, we can predict its properties and verify those predictions against observations. And yet the understanding that simulations provide is not complete. The simulations include dark matter, but we do not know what dark matter is. They include dark energy, the mysterious force that accelerates the expansion of the universe, but we do not understand its nature. They reproduce the cosmic web, but they rely on initial conditions, the primordial fluctuations, whose ultimate origin lies in physics we have not yet mastered. The simulations work, but they work partly because they include parameters we have measured but not explained. The cosmic web, even as we understand its formation, points toward deeper questions that remain unanswered. The growth of structure in the universe is also not a simple story of accumulation. It is a story of competition between two opposing forces. On one hand, gravity pulls matter together, building structure, concentrating mass, creating the nodes and filaments of the web. On the other hand, the expansion of the universe pulls matter apart, diluting density, stretching space, working against the formation of structure. The history of the cosmos is the history of this competition, and the balance between these forces has not remained constant. In the early universe, gravity had the upper hand. The expansion was rapid, but the density of matter was high, and gravity could overcome the expansion to form structures at an accelerating pace. But approximately 5 billion years ago, something changed. The expansion of the universe, which had been slowing due to the gravitational attraction of matter, began to accelerate. The cause is what we call dark energy, a property of space itself that produces a repulsive effect, pushing the universe apart faster and faster over time. The discovery of this acceleration, announced in 1998 by two independent teams studying distant supernovae, was one of the most surprising findings in the history of cosmology. It earned the 2011 Nobel Prize in Physics and fundamentally altered our understanding of the universe's fate, and it has profound implications for the cosmic web. As the expansion accelerates, it becomes increasingly difficult for gravity to form new structures. The cosmic web, in a sense, is freezing. The large-scale architecture that exists today, the filaments, the clusters, the superclusters, the voids, represents something close to the final form of cosmic structure. Future matter cannot fall across voids that are expanding faster than it can travel. Future filaments cannot form where space stretches faster than gravity can contract. The cosmic web we observe is not a snapshot of a moment in an ongoing process. It is the high water mark of cosmic structure, the most elaborate architecture that gravity will ever build, preserved in a universe that is slowly but inexorably pulling itself apart. This realization casts the cosmic web in a different light. We are not observing a young universe, still forming, still evolving towards a more complex future state. We are observing a universe that has already achieved its greatest structural complexity, that is now slowly dissolving into an ever more uniform emptiness. The cosmic web is not a beginning. It is, in some sense, a culmination, the peak of a mountain that the universe climbed over billions of years and from which it is now inevitably descending. The surveys that revealed the cosmic web have also mapped this evolution across cosmic time. Because light travels at a finite speed, distant galaxies are seen not as they are now, but as they were when their light began its journey. A galaxy 1 billion light-years away appears as it was 1 billion years ago. A galaxy 10 billion light-years away appears as it was 10 billion years ago, when the universe was less than 4 billion years old. By observing galaxies at different distances, astronomers can effectively watch the cosmic web evolve, comparing its structure in the early universe to its structure today. What these observations reveal is a universe that was once far more active. In the early cosmos, gas streamed along filaments at prodigious rates. feeding young galaxies and fueling the formation of stars. The cosmic web was a highway system for matter, a network of supply lines that delivered the raw material from which galaxies were built. The densest filaments channeled rivers of gas toward massive clusters still in formation, creating conditions that would later produce the most extreme environments in the universe. The hearts of galaxy clusters, where millions of galaxies swarm in gravitationally bound clouds of hot gas and dark matter. The surveys also reveal the remains of this activity. Galaxies that grew fat on the matter delivered by filaments, galaxies that exhausted their gas supplies and faded from star-forming spirals to red and dead ellipticals, galaxies that collided with neighbours along crowded filaments and merged into bloated giants far larger than the Milky Way. The cosmic web is not merely a structure, it is a history, written in the positions and properties of galaxies, readable by those with the instruments and patience to decode it. But the filaments carry more than history. They carry matter in motion, matter that is still falling toward the densest nodes, matter that traces the flow of cosmic evolution. By measuring the velocities of galaxies, not just their positions, astronomers can reconstruct the gravitational field that drives this flow. They can map the valleys and hills of the cosmic gravitational landscape, identifying the regions that attract matter and the regions that repel it. This technique, called velocity field reconstruction, has revealed structures invisible to direct imaging, concentrations of mass that exert gravitational influence but cannot be seen because they are obscured by the dust and gas of our own galaxy. The most famous of these hidden structures is the Great Attractor, a gravitational anomaly in the direction of the constellation Centaurus that appears to be pulling the Milky Way and thousands of neighbouring galaxies toward it at several hundred kilometres per second. For decades, the Great Attractor was a mystery, hidden behind the zone of avoidance, the region of sky obscured by the disk of the Milky Way, where dust and stars block our view of the distant universe. Only through indirect methods, velocity measurements, X-ray observations, infrared surveys that could peer through the dust, did astronomers gradually map its location and extent. The Great Attractor turns out to be a component of a much larger structure, the Laniakea supercluster, mapped in 2014 by R. Brent Tully and his colleagues using the same velocity field techniques. Laniakea, whose name means immense heaven in Hawaiian, contains the Milky Way, the Virgo cluster, the Great Attractor, and approximately 100,000 galaxies spread across 500 million light-years. It is not a stable structure. It will eventually disperse as dark energy tears it apart. But for now, it represents the gravitational basin within which our galaxy resides, the region of the cosmic web that defines our cosmic neighbourhood. The discovery of Laniakea illustrates how much the mapping of the cosmic web has revealed about our place in the universe. Before these surveys, we knew the Milky Way was part of the Local Group, a modest collection of galaxies dominated by ourselves and Andromeda. We knew the Local Group was part of the Virgo supercluster, a larger association whose centre lay in the direction of the Virgo cluster. But we did not know that Virgo was merely an outskirt, a suburb of a much larger supercluster whose true centre lay elsewhere. We did not know that our motion through space was dominated by the gravitational pull of structures we could not even see. The cosmic web, as mapped by modern surveys, has revealed that our cosmic address is longer and more complicated than we once imagined, that we are embedded in structures within structures within structures, each one larger and less obvious than the last. And yet, even Laniakea is not the final word. Beyond it lie other superclusters, the Shapley supercluster, the Perseus-Pisces supercluster, the Horologium supercluster, each a gravitational basin in its own right, each connected to others by the gossamer threads of cosmic filaments. The surveys have mapped these structures, traced their connections, measured their motions. They have revealed the cosmic web not as a single coherent system, but as a patchwork of interlinked domains, each with its own internal dynamics, each participating in the larger flow of cosmic evolution. The voids between these superclusters are equally revealing. Unlike the dense nodes where galaxies congregate, voids are regions of profound emptiness, stretching hundreds of millions of light-years across. Yet even voids are not perfectly empty. Within them, astronomers have found small galaxies, isolated, dim, often irregular in shape, that inhabit environments radically different from those in clusters or filaments. These void galaxies have evolved in isolation, without the collisions and interactions that shaped galaxies in denser regions. They provide natural laboratories for studying galaxy evolution in the absence of environmental influences, revealing what galaxies would become if left entirely to themselves. The voids also push against their surroundings. As matter drains away from voids and accumulates in filaments and clusters, the voids expand, their underdensity becoming more pronounced over time. This expansion creates compression at the boundaries, where void meets filament, squeezing matter together and potentially triggering star formation in galaxies along the edges. The cosmic web is not static. It breathes. Matter flows along its filaments, accumulates at its nodes, drains away from its voids. The entire structure is in motion, evolving, changing, even as dark energy gradually freezes its largest features into permanence. The surveys that revealed all of this, the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, the more recent dark energy spectroscopic instrument, represent one of the great scientific achievements of our era. They have transformed cosmology from a discipline of speculation and inference into a precision science capable of mapping the universe at scales that would have seemed fantastical only decades ago. The cosmic web, once a theoretical prediction, is now an observed reality. Documented in databases containing millions of galaxies, visualized in images and simulations that make its structure accessible to anyone with an internet connection. But the surveys have also raised new questions. They have measured the cosmic web with enough precision to reveal subtle tensions between observations and predictions. The rate at which structure grows, the rate at which gravity concentrates matter into denser regions, can be inferred from the cosmic web's present configuration. When scientists compare this growth rate to predictions from the standard cosmological model, small discrepancies appear. These discrepancies might be statistical flukes, errors in the data, or limitations in the simulations. But they might also be hints of new physics, indications that our understanding of gravity, dark matter, or dark energy is incomplete. The cosmic web, in other words, is not just a subject of study. It is a probe, a tool for testing the foundations of physics at scales where no laboratory experiment can reach. By measuring the web's structure with increasing precision, by comparing observations to ever more sophisticated simulations, cosmologists hope to detect subtle departures from known physics that might reveal new fundamental principles. The cosmic web is a message from the universe, written in a language of gravity and expansion, and we're still learning to read it. And reading that message requires us to confront something that most visualizations of the cosmic web do not convey: the sheer, overwhelming scale of what we are looking at. We have discussed galaxies as though they were points of light scattered across a map, as though superclusters were merely larger collections of these points, as though filaments were simple threads connecting node to node. But this language, however convenient, obscures a truth so staggering that even the scientists who study these structures sometimes struggle to hold it fully in their minds. The cosmic web is not just large. It is large in a way that requires us to abandon our normal relationship with scale entirely. Consider a single galaxy. Not the Milky Way, with its familiar spiral arms and central bulge, but a typical spiral galaxy somewhere in the cosmic web, one of the hundreds of billions that populate the observable universe. This galaxy contains perhaps 200 billion stars, each one a sun in its own right, many with planets, some potentially harbouring conditions suitable for life. Light, travelling at 300,000 kilometres per second, requires 100,000 years to cross this galaxy from edge to edge. If you were to begin your journey across this galaxy when the first anatomically modern humans appeared in Africa, you would arrive at the opposite side roughly today, 100,000 years of travel at the fastest speed the universe permits, and you would have crossed a single galaxy, one of hundreds of billions. Now consider that the nearest large galaxy to the Milky Way, the Andromeda Galaxy, lies 2.5 million light-years away. The light reaching our telescopes tonight left Andromeda when our ancestors were still learning to shape stone tools, before the genus Homo had diversified into its many species, before anything we would recognize as human culture existed. 2.5 million years of light travel to reach our nearest major neighbour. And Andromeda is, by cosmic standards, essentially next door. It is part of our local group, gravitationally bound to the Milky Way, destined to merge with us in 4.5 billion years. The local group itself spans roughly 10 million light-years. Step outside this neighbourhood and you enter the Virgo cluster, containing over 1,000 galaxies, spanning roughly 15 million light-years in diameter. The Virgo cluster is the nearest large cluster to the local group, the gravitational anchor around which our corner of the universe turns, and yet the Virgo cluster is merely a single node in a much larger structure. The Virgo supercluster, later recognised as part of the even larger Laniakea supercluster, which spans 500 million light-years from edge to edge. 500 million light-years. The number is easy to say, easy to type, but nearly impossible to comprehend. Light travelling since before the Cambrian explosion, since before the first animals with hard shells appeared in Earth's oceans, since before fish or insects or plants capable of photosynthesis colonised the land, would only now be arriving at the opposite side of Laniakea. The entire history of complex life on Earth, from the first trilobites to the smartphones in our pockets, fits within the time it takes light to cross our home supercluster. And Laniakea is merely one supercluster among many. The filaments that connect these superclusters, the threads of the cosmic web that the surveys have revealed in such painstaking detail, are themselves structures of almost incomprehensible dimension. A typical filament stretches between 200 and 500 million light-years in length, sometimes longer. The width of these filaments, the thickness of these cosmic threads, ranges from roughly 10 to 50 million light-years. These are not thin strands in any meaningful sense. They are structures that could contain thousands of Milky Way-sized galaxies arranged side by side across their breadth. We call them filaments because they are elongated relative to their other dimensions, because they connect larger structures like threads in a web. But each filament is itself a cosmos, a universe of galaxies flowing along gravitational channels toward distant destinations. The voids between these filaments are even more staggering in their emptiness. A typical cosmic void spans 100 to 300 million light-years across, though the largest known voids exceed 1 billion light-years in diameter. The Bhuta's void, one of the first to be systematically studied, spans approximately 330 million light-years and contains so few galaxies that its discovery in 1981 prompted genuine shock in the astronomical community. Scientists had not expected the universe to be capable of such profound emptiness. They had not anticipated that matter could evacuate a region so completely that light itself, travelling across the void, would find almost nothing to illuminate. To put this emptiness in perspective, consider that if the Milky Way were located at the centre of the Bhuta's void rather than in the relatively dense environment of the Virgo supercluster, we would have discovered the existence of other galaxies much later in our scientific history. The nearest galaxy would lie so far away that until the development of large modern telescopes, we might have believed ourselves alone in the universe, not just the only intelligent species, but the only galaxy. The night sky would have appeared populated only by the stars of our own Milky Way, with no hint of the billions of other island universes scattered across space. The Bhuta's void is not a gap in the cosmic web. It is an abyss, a region where the universe chose to place almost nothing at all. And yet, as we noted, even the voids are not perfectly empty. Scattered within them are small galaxies, dwarf galaxies, irregular galaxies, isolated spirals that never experienced the collisions and mergers that shaped their counterparts in denser regions. These void galaxies are among the most isolated objects in the observable universe, some sitting tens of millions of light-years from their nearest neighbour. They have evolved in cosmic solitude, their stellar populations undisturbed by gravitational interactions, their gas reserves intact, their histories unmarked by the violence that shaped galaxies in clusters and groups. Studying these isolated void galaxies provides insights that cannot be obtained from examining galaxies in denser environments. When a galaxy evolves in isolation, it becomes a control sample, a baseline against which the effects of environment can be measured. Astronomers have found that void galaxies tend to be bluer than their cluster counterparts, indicating ongoing star formation. They contain more gas, having lost less of their fuel to tidal stripping or ram pressure from intergalactic medium. They rotate more slowly, their dark matter halos less concentrated than those of galaxies that have experienced repeated interactions. Each of these differences tells a story about how environment shapes galactic evolution, about how a galaxy's position within the cosmic web determines its fate as surely as its initial mass or composition. The boundaries between voids and filaments are regions of particular interest. Here, Matter compressed by the expanding void meets matter falling into the filament, creating zones of enhanced density and activity. Some simulations predict that these boundary regions should exhibit increased rates of star formation, as gas clouds collide and compress under the competing gravitational influences. Others suggest that these regions might host unusual galaxy populations, transition objects caught between the isolation of the void and the crowded turbulence of the filament. Observational surveys are only now beginning to map these boundary regions in sufficient detail to test these predictions, to understand what happens when void meets web. The flow of matter along filaments is another phenomenon that the surveys have begun to quantify. Galaxies do not merely sit within filaments like beads on a string, they move, falling along the filament toward the nearest cluster or supercluster node, their velocities determined by the gravitational potential of the matter ahead. This flow can be measured through careful analysis of galaxy redshifts, distinguishing the component of velocity caused by cosmic expansion from the component caused by local gravitational attraction. The results reveal rivers of galaxies streaming through the cosmic web, tributaries feeding into larger flows, entire galactic populations migrating across hundreds of millions of light years toward gravitational destinations they will not reach for billions of years. The velocities involved are substantial, typically several hundred kilometers per second relative to the smooth expansion of space, sometimes exceeding 1,000 kilometers per second for galaxies falling into the largest clusters. The Milky Way itself participates in this flow, moving at roughly 600 kilometers per second toward the Great Attractor, while simultaneously being pulled by the Shapley concentration beyond it. We are passengers on a galactic raft, drifting along the currents of the cosmic web, our trajectory determined by the distribution of matter on scales we can barely perceive. This motion creates subtle but measurable effects in the cosmic microwave background, the leftover radiation from the Big Bang that fills all of space. As our local group moves through this radiation, we observe a slight Doppler shift, a blue shift in the direction of our motion, and a red shift behind us. This dipole anisotropy, as it is called, provides independent confirmation of our velocity through space, a cosmic speedometer that complements the galaxy surveys. The agreement between these different measurements is remarkable, a testament to the consistency of our cosmological model. We know not only that we are moving, but how fast and in what direction, thanks to the complementary observations of galaxies and primordial radiation. But the cosmic web is not merely a passive structure through which galaxies flow. It is an active environment that shapes the galaxies passing through it. As a galaxy falls along a filament toward a cluster, it encounters the intergalactic medium, the tenuous gas that fills the space between galaxies within the web. This gas, though incredibly sparse by any terrestrial standard, exerts pressure on galaxies moving through it at high speed. The process, known as ram pressure stripping, can remove gas from a galaxy's outer regions, cutting off the fuel supply needed for continued star formation. A galaxy entering a cluster may lose most of its cold gas within a few 100 million years, transforming from a vibrant star-forming spiral into a quiescent elliptical incapable of producing new stars. The evidence for this transformation is visible in the populations of galaxies at different positions within the cosmic web. Galaxies in clusters are predominantly red, their stellar populations old, their star formation long since ceased. Galaxies in filaments show intermediate colours, some still forming stars, others already quenched. Galaxies in voids tend to be blue, their star formation ongoing, their gas reserves largely intact. This environmental dependence is one of the clearest signatures of how position within the cosmic web determines galactic evolution, how the large-scale structure of the universe imprints itself on the smallest details of individual galaxies. Yet the influence runs both ways. Galaxies are not merely passive recipients of environmental effects. They also shape their environments through the energy they release. Supernovae explode within galaxies, driving winds that carry metals and energy into the surrounding medium. Black holes at galactic centres grow by accreting matter, releasing radiation and jets that heat the intergalactic gas for millions of light years around. These feedback processes, the term astronomers use for the way galaxies influence their surroundings, regulate the flow of gas into and out of galaxies, modulating star formation rates and chemical evolution. The most massive black holes, found at the centres of the largest galaxies and cluster cores, can heat the surrounding gas so efficiently that they prevent it from cooling and forming new stars. Without this heating, Simulations predict that the most massive galaxies should be much more massive still, their star formation running away in a cascade of cooling gas and stellar birth. The fact that observed galaxies are less massive than this naive prediction suggests that black hole feedback must be operating, injecting energy into the environment and regulating the growth of the larger structures. The cosmic web is not just a scaffolding on which galaxies form, it is an ecosystem in which galaxies and their environments evolve together, each shaping the other in a complex dance of gravity, gas, and energy. Understanding this ecosystem requires simulations of unprecedented scale and sophistication. Modern cosmological simulations track the evolution of dark matter, gas, and stars from shortly after the Big Bang to the present day, following billions of particles as they interact gravitationally and hydrodynamically. Projects like Illustris TNG, Eagle, and Simba have produced synthetic universes that can be compared directly to observations, generating mock galaxy surveys that mimic the data from SDSS or DESI. These simulations reproduce the cosmic web with remarkable fidelity. The filaments, voids, clusters, and superclusters emerge naturally from the physics of gravity and gas dynamics, confirming that our theoretical understanding of structure formation is fundamentally correct. But the simulations also reveal how much we do not know. The details of star formation within galaxies, the processes that convert gas into stars on scales of a few light years, cannot be simulated directly in cosmological codes that span billions of light years. Instead, modelers must use simplified prescriptions, subgrid recipes that approximate these processes based on local conditions. The choice of these prescriptions affects the results dramatically. Different simulation projects using different subgrid models produce galaxy populations with noticeably different properties. The colours of galaxies, their sizes, their star formation rates, their metal content, all depend on modelling choices that are not yet fully constrained by first principles. This uncertainty represents one of the frontiers of modern astrophysics. The cosmic web, with its enormous range of scales and its complex interactions between gravity, gas, radiation, and magnetic fields, poses a computational and theoretical challenge that will occupy researchers for decades to come. Each new observation from surveys like DESI or upcoming missions like the Vera C, Rubin Observatory's legacy, survey of space and time adds constraints, narrowing the range of acceptable models, pushing simulations toward greater accuracy. The goal is not merely to reproduce what we observe, but to predict what we will observe next, to use simulations as theoretical laboratories for testing ideas before observations can confirm or refute them. The information encoded in the cosmic web extends beyond the distribution of galaxies. The subtle alignments of galaxies, the orientations of their spin axes relative to nearby filaments, contain clues about how angular momentum was acquired during galaxy formation. Observations suggest that galaxies tend to spin perpendicular to nearby filaments, their rotation axes aligned along the filament direction, as though the tidal forces of the filament imprinted a preferred direction on the collapsing gas that formed them. This alignment is weak, only a statistical tendency visible when many galaxies are combined, but it represents a direct connection between the largest structures in the universe and the internal properties of individual galaxies. Similarly, the shapes of galaxies correlate weakly with the direction toward nearby large-scale structures, as tidal forces stretch and compress the dark matter halos within which galaxies form. These intrinsic alignments, as they are called, create a systematic effect that must be carefully modelled when using galaxy shapes to measure gravitational lensing. Weak lensing surveys seek to map the distribution of dark matter by detecting the subtle distortions in galaxy shapes caused by the gravitational bending of light. But if galaxies are intrinsically aligned with the cosmic web, this alignment mimics the lensing signal, potentially biasing measurements of dark matter distribution and cosmic expansion. Separating the true lensing signal from the intrinsic alignment signal requires detailed understanding of how galaxies form within the cosmic web, connecting observations across an enormous range of scales. The cosmic web also serves as a laboratory for testing fundamental physics in ways no terrestrial experiment can match. The voids of the cosmic web, with their extreme emptiness, probe the behaviour of gravity in regions of very low density. General relativity predicts specific effects in such regions, including the integrated Sachs-Wolf effect, which leaves an imprint on the cosmic microwave background as photons traverse evolving voids. Measuring this effect provides tests of general relativity on scales of hundreds of millions of light-years in environments utterly unlike the high-density regions where gravity is most commonly tested. The filaments themselves may host imprints of physics from the earliest moments of the universe. The same quantum fluctuations that seeded the formation of the cosmic web might have created topological defects, cosmic strings, domain walls, or other exotic structures that could affect how matter clusters on large scales. The precise statistics of the cosmic web, the distribution of filament lengths, void sizes, and cluster masses, depend sensitively on the initial conditions from which structure grew. By measuring these statistics with sufficient precision, cosmologists hope to constrain not just the standard model of cosmology, but also modifications to it, including alternative theories of gravity, additional species of dark matter, or traces of physics from the inflationary epoch that preceded the Big Bang. The observable universe, as revealed by the surveys, contains roughly 200 billion galaxies. Perhaps more, perhaps fewer, as estimates continue to be refined. These galaxies are not distributed randomly, nor uniformly, nor in any simple pattern that could be described in a few words. They are arranged in a foam-like structure of extraordinary complexity, a structure that preserves information about the physics of the early universe while also recording the subsequent 14 billion years of gravitational evolution. The cosmic web is simultaneously a fossil record of the Big Bang and a living document of ongoing cosmic change, written in a language of gravity and expansion, encoded in the positions and motions of hundreds of billions of galaxies scattered across billions of light-years of space. And yet, for all its complexity, the cosmic web exhibits a remarkable statistical simplicity at the larger scales. The universe, averaged over sufficiently large volumes, is homogeneous and isotropic, the same in every direction, the same at every location. This cosmic principle, assumed by cosmologists since the earliest days of relativistic cosmology, has been confirmed observationally with increasing precision. Look in any direction and count galaxies in sufficiently large volumes, and you will find roughly the same number. The cosmic web, despite its local complexity, smooths out at the grandest scales, revealing an underlying uniformity that makes cosmology possible as a science. This uniformity has limits. The transition from the complex filamentary structure visible on scales of tens of millions of light-years to the smooth, homogeneous distribution visible on scales of hundreds of millions of light-years defines a characteristic scale of cosmic structure, the scale of homogeneity. Current measurements place this scale at roughly 200 to 300 megaparsecs, or roughly 600 million to 1 billion light-years. Above this scale, the universe is smooth. Below it, the universe is dominated by the intricate architecture of the cosmic web. The existence of this scale raises profound questions about the ultimate nature of cosmic structure. Why does the universe become homogeneous at this particular scale and not some other? What determines the characteristic sizes of filaments, voids, and superclusters? These questions connect the observed cosmic web to the physics of the early universe, to the spectrum of primordial fluctuations generated during inflation, to the nature of dark matter and dark energy. Every measurement of the cosmic web is simultaneously a measurement of these fundamental quantities, a window into physics that cannot be accessed by any other means. The surveys have shown us what the universe looks like. They have mapped the cosmic web across billions of light-years, revealing structures larger than anything we had imagined before their discovery. They have confirmed theoretical predictions and raised new puzzles. They have transformed our understanding of our place in the cosmos, showing us that we inhabit not a random scatter of galaxies, but a coherent structure, a web of gravity and matter that connects everything to everything else across the observable universe. But showing us what the universe looks like is not the same as showing us what it means. The cosmic web is a fact of nature, an observed phenomenon as real as mountains or oceans or the sun rising in the east. Yet it is also a mystery, a structure whose existence demands explanation, whose properties encode information about the deepest laws of physics. The surveys have given us the map. Now we must learn to read it, to extract from the positions and motions of 1 trillion galaxies the secrets of cosmic origins and destiny. The cosmic web is not static. This is perhaps the most profound revelation that follows from understanding its nature, yet it is also the easiest to overlook. When we speak of filaments stretching hundreds of millions of light years, when we describe voids spanning volumes that dwarf entire galaxy clusters, the sheer scale of these structures can create an illusion of permanence. Surely something so vast must be eternal, unchanging across the brief span of human observation. Surely the cosmic web we map today is the cosmic web that has always existed and will always exist. This intuition is understandable. It is also entirely wrong. The cosmic web is evolving. It has been evolving since the first moments after the Big Bang, and it will continue evolving for as long as the universe exists. The filaments we observe today are not the filaments that existed 1 billion years ago, and they are not the filaments that will exist 1 billion years hence. The voids are growing. The clusters are accreting. The superclusters are fragmenting even as they form. The entire architecture of the universe is in slow, relentless motion, a motion so gradual that no human lifetime could perceive it, yet so inexorable that given sufficient time it will transform every structure we have mapped into something unrecognizable. Understanding this evolution requires understanding the forces that drive it. Two competing influences shape the fate of the cosmic web, locked in a gravitational dance that has been playing out since the universe began. The first is gravity itself, the attractive force that pulls matter toward matter, that causes galaxies to fall toward each other, that builds filaments and clusters from the diffuse primordial gas. Gravity is the architect of structure, the force that transforms uniform matter into complex patterns, that carves the cosmic web from the smooth fabric of the early universe. Without gravity, there would be no filaments, no clusters, no galaxies, no stars, no planets, no observers to contemplate the cosmos. Gravity is the great organizer, the fundamental force that makes complexity possible. The second influence is cosmic expansion, the stretching of space itself that carries galaxies apart, that dilutes matter across ever larger volumes, that works against gravity's constructive efforts. The universe is expanding, and this expansion is not merely a motion of galaxies through space, but a genuine increase in the amount of space between them. As space stretches, the density of matter decreases. As density decreases, gravity's grip weakens. Cosmic expansion is the great disperser, the force that prevents gravity from collapsing everything into a single point, that maintains the vast emptiness between structures, that ensures the universe remains mostly void rather than mostly matter. These two forces, gravity pulling inward, expansion pushing outward, have been in tension since the beginning. The history of the cosmic web is the history of their competition, their balance, their shifting dominance over cosmic time. In the earliest epochs, when the universe was young and dense, gravity held the upper hand. Matter fell together rapidly, forming the first dense knots that would become the seeds of galaxies and clusters. The cosmic web was being born, its filaments thickening, its nodes condensing, its structure becoming more pronounced with each passing eon. But as the universe expanded and matter dispersed, this gravitational growth began to slow. The rate of structure formation peaked and then declined, not because gravity weakened in any fundamental sense, but because matter became too sparse for gravity to work efficiently. The cosmic web was still growing, but more slowly, more grudgingly, fighting against an expansion that was stretching space faster than gravity could pull matter together. And then, roughly 5 billion years ago, something changed. The expansion of the universe began to accelerate. This was not a gradual shift, not a minor adjustment in the balance of cosmic forces, but a fundamental transformation in the nature of cosmic evolution. The cause was dark energy, the mysterious component of the universe that had always been present, but whose effects only became dominant as the universe aged and matter diluted. Dark energy does not dilute with expansion, the way ordinary matter and radiation do. Its density remains roughly constant as space stretches, which means its influence grows relative to matter's as the universe expands. When the universe was young and dense with matter, dark energy was negligible, a faint whisper against the roar of gravity. But as matter diluted over billions of years of expansion, dark energy's whisper became a shout, and eventually it became the dominant voice shaping cosmic evolution. The implications for the cosmic web are profound. In a universe dominated by dark energy, cosmic expansion accelerates, and this acceleration works against structure formation at every scale. Filaments that would have grown denser under gravity's influence instead find their growth stunted. Clusters that would have accreted more galaxies instead find those galaxies carried away by accelerating expansion. The cosmic web, which had been growing more intricate and connected throughout the early history of the universe, is now beginning to unravel. The process is slow by any human measure. Billions of years, hundreds of billions of years, stretching toward timescales that dwarf the current age of the cosmos. But the direction is clear. The cosmic web is not eternal. It is transient, a structure that arose from the interplay of gravity and expansion in a specific epoch of cosmic history, and that will ultimately dissolve as expansion overwhelms gravity entirely. This dissolution is already visible in the simulations that cosmologists run on the world's most powerful supercomputers. These simulations evolve the cosmic web forward in time, extrapolating the physical laws we have measured into the cosmic future. They show filaments gradually thinning as their constituent galaxies drift apart. They show voids expanding, merging with neighbouring voids, swallowing the increasingly sparse filaments that once separated them. They show clusters becoming isolated islands in an increasingly empty sea, their connections to the larger cosmic web severed by the relentless stretching of space. On timescales of hundreds of billions of years, the cosmic web will become a cosmic archipelago, scattered clusters and galaxy groups separated by voids so vast and so empty that no signal could ever cross them. But the ultimate fate of the cosmic web stretches beyond even this dissolution. As expansion continues to accelerate, the isolated clusters themselves will eventually come apart. Galaxies that are currently gravitationally bound to each other will find their bonds stretched beyond breaking. The expansion of space will overcome even the gravity that holds galaxy groups together, and individual galaxies will drift into their own private volumes of space, forever separated from their former companions. Eventually, on timescales that dwarf even the 100-billion-year dissolution of the cosmic web, expansion will overcome the gravity that holds individual galaxies together. Stars will drift apart. Solar systems will dissolve. The cosmic web will not merely thin and fragment, it will cease to exist in any meaningful sense, replaced by a universe of isolated particles drifting through an emptiness so complete that the concept of structure itself will become meaningless. This is a future so remote that it seems almost theoretical, a mathematical extrapolation rather than a physical reality. Yet the physics that predicts this future is the same physics that explains the cosmic web we observe today. The simulations that show the web's ultimate dissolution are the same simulations that accurately reproduce its current structure. We cannot accept the cosmic web's present form as real, while dismissing its future evolution as speculation. The web we have mapped is a snapshot in time, a moment captured in the ongoing evolution of cosmic structure. To understand the web is to understand its past and its future, to see it not as a fixed architecture but as a flowing pattern, a river of matter caught in a photograph that freezes its motion, but cannot capture its destination. The cosmic web's evolution is not merely a matter of distant futures. It is visible in the present, encoded in the differences between the nearby universe and the universe as it appeared billions of years ago. When astronomers observe distant galaxies, they are looking back in time, seeing the universe as it was when the light they observe was emitted. A galaxy 10 billion light-years away appears not as it is today, but as it was 10 billion years ago, when the universe was young, when the cosmic web was still forming, when gravity's dominance over expansion was at its peak. By comparing nearby and distant regions of the universe, astronomers can watch the cosmic web evolve in real time, or rather in real cosmic time, observing the same structures at different stages of their development. The differences are striking. The distant universe, the universe as it was 8, 10, 12 billion years ago, was denser than today. Filaments were narrower but more numerous. Voids were smaller but more crowded with gas that had not yet been fully expelled. Galaxies were closer together, interacting more frequently, merging at rates far higher than we observe in the local universe. The cosmic web of the early universe was a more dynamic, more turbulent structure than the mature web we inhabit today, a web still in the throes of active construction, rather than the gradual dissolution that characterizes our current epoch. This evolution is quantifiable. Astronomers measure a quantity called the two-point correlation function, which describes the statistical clustering of galaxies as a function of distance. A higher correlation means stronger clustering, more pronounced structure, a more sharply defined cosmic web. Measurements of this correlation function at different cosmic epochs show a clear trend. Clustering was weaker in the very early universe, when primordial fluctuations had not yet had time to grow. It strengthened through the first several billion years as gravity built structure, and it has been gradually weakening again as dark energy begins to dominate and expansion overwhelms gravitational growth. The cosmic web today is not at its densest, not at its most structured. It has already passed its peak, and the web we observe is already beginning its slow dissolution. We live in the autumn of cosmic structure formation, not its summer, and certainly not its spring. This temporal evolution adds another dimension to our understanding of the cosmic web. The surveys have mapped the web in 3 spatial dimensions, revealing its filamentary architecture across the observable universe. But there is a 4th dimension to this map, a dimension of time, accessible through the look-back that accompanies distance. The Sloan Digital Sky Survey, the 2-micron All-Sky Survey, the various successors and extensions and complementary programs. All of these surveys sample not just the spatial structure of the cosmic web but also its temporal evolution. Every galaxy in the catalogue carries 2 pieces of information encoded in its light, where it is and when it was. The map is not merely a map of space but a map of space-time, a 4-dimensional representation of cosmic structure that spans not just billions of light years but billions of years of cosmic history. Reading this 4-dimensional map requires sophisticated statistical techniques. The light from distant galaxies is fainter, redder, harder to observe than light from nearby galaxies. Selection effects creep in, biasing surveys towards certain types of galaxies at certain distances. Separating true cosmic evolution from observational artifacts requires careful modelling, extensive calibration, painstaking attention to the details of telescope performance and atmospheric conditions and data processing pipelines. The cosmic web revealed by the surveys is not a raw image but a highly processed inference, a reconstruction built from millions of individual observations filtered through sophisticated statistical machinery. The beauty of this process is that it works. The cosmic web we reconstruct from survey data matches the cosmic web predicted by our theoretical models. The evolution we infer from comparing nearby and distant regions follows the trajectories predicted by simulations. The consistency between observation and theory, between inference and prediction, gives us confidence that we are genuinely mapping reality, rather than artifacts of our measurement process. The temporal dimension of the cosmic web raises questions that pure spatial mapping cannot answer. Why did structure form when it did? Why did the cosmic web reach its peak complexity when the universe was roughly half its current age rather than younger or older? These questions connect the observed evolution of the cosmic web to the fundamental parameters of cosmology: the density of matter, the density of dark energy, the expansion history of the universe. The timing of cosmic structure formation is not arbitrary. It is determined by the same parameters that determine the geometry of the universe, the fate of cosmic expansion, the ultimate destiny of everything that exists. Measuring the cosmic web at different epochs is therefore a way of measuring these fundamental parameters, a technique that complements other cosmological probes like the cosmic microwave background or supernova distances. The cosmic web is also connected to phenomena that play out on timescales far shorter than cosmic evolution. The filaments and nodes of the web are not inert scaffolding, but active environments where galaxies are transformed by their surroundings. A galaxy falling into a cluster experiences a radically different history than a galaxy drifting through a void. The cluster environment is hostile to star formation, hot intracluster gas, high-velocity encounters with other galaxies, tidal forces that strip away galactic envelopes and trigger bursts of activity before ultimately quenching the galaxy into passive senescence. Void galaxies, by contrast, evolve in isolation, forming stars at a leisurely pace, maintaining their gas reservoirs across cosmic time, remaining blue and active while their cluster counterparts redden and die. The cosmic web is therefore not merely a spatial arrangement of matter, but a determining factor in the evolutionary paths of the galaxies that compose it. This connection between environment and evolution is visible in the statistics of galaxy populations. Red, dead, elliptical galaxies are preferentially found in clusters, the dense nodes where filaments converge. Blue, star-forming spiral galaxies are preferentially found in filaments and fields, the moderate density regions between clusters and voids. The reddest, Most gas-poor, most spheroidal galaxies of all are found at the very centres of the most massive clusters, where environmental influences are most extreme. The cosmic web is a map of galactic fate, a guide to which galaxies will thrive and which will wither, determined by the accident of where each galaxy happens to have formed within the larger structure. The physical processes that drive these environmental differences are increasingly well understood. Ram pressure stripping occurs when a galaxy falls through the hot gas that pervades galaxy clusters. The intergalactic medium acts like a headwind, pushing against the galaxy's own gas reservoir, stripping away the cold gas from which stars form. A galaxy can lose its entire gas supply in a single passage through a cluster centre, a cosmic mugging that takes only a few 100 million years but permanently alters the galaxy's evolutionary trajectory. Harassment occurs when a galaxy experiences repeated high-velocity encounters with other cluster members, tidal forces yanking at its structure, heating its disk, transforming its spiral arms into a smoother, more spheroidal configuration. Starvation occurs when a galaxy's supply of fresh gas is cut off, either by ram pressure or by gravitational interactions that remove its extended gas halo. Without new gas falling in, the galaxy gradually exhausts its existing reservoir, forming fewer and fewer stars until activity ceases entirely. These processes operate differently in different environments, and the cosmic web maps those environments with exquisite precision. The density of the local cosmic web determines which processes dominate, how quickly they act, how completely they transform the galaxies they affect. A galaxy in a cluster's outskirts experiences gentler treatment than one at the centre. A galaxy in a filament experiences different influences than one in a void. The cosmic web is a sorting machine, directing galaxies into different evolutionary channels based on their positions within its structure. The filaments themselves are not merely conduits, but active participants in this sorting process. Gas flowing along filaments into clusters can fuel new star formation, even as other environmental processes work to quench it. The balance between fueling and quenching depends on the details of filament structure, on the velocity of infalling material, on the geometry of the cosmic web in each particular region. Some filaments deliver fresh gas efficiently, maintaining star formation in the galaxies that accrete along their lengths. Others deliver gas that is too hot, too diffuse, or too turbulent to fuel new stars. The cosmic web is not uniform in its effects, and mapping its structure is essential to understanding why galaxies in different environments have followed such different evolutionary paths. The connection between cosmic structure and galactic evolution extends to supermassive black holes, the monstrous objects that lurk at the centres of most massive galaxies. These black holes are fed by gas falling toward galactic centres, and the availability of that gas depends on the cosmic environment. Cluster galaxies, stripped of their gas reservoirs, tend to host quiescent black holes that rarely activate into powerful quasars. Field galaxies, rich in gas, can host active black holes that outshine entire galaxies when they flare into activity. The cosmic web influences not just the stars in galaxies, but the gravitational monsters at their hearts, determining which black holes grow rapidly and which remain dormant, which pour energy into their surroundings and which sit quietly in darkness. The surveys have mapped not just galaxies but quasars, the most luminous manifestations of active black holes. These quasars trace the cosmic web in a distinctive pattern, different from the pattern traced by ordinary galaxies. Quasars were more common in the past, when the universe was denser and gas was more abundant. They are found preferentially in certain environments, neither the densest cluster centres nor the emptiest voids, but somewhere in between, in the regions where gas supplies remain available. But mergers and interactions trigger the infall that activates the black holes. Mapping quasars across cosmic time reveals another facet of the cosmic web's evolution, another window into the processes that shape the universe we observe. The filamentary structure of the universe is therefore not merely a curiosity, not merely an aesthetic feature of cosmic maps. It is a key to understanding everything that happens within it. The positions of galaxies are determined by the cosmic web. The properties of galaxies are determined by the cosmic web. The activity of supermassive black holes is determined by the cosmic web. The distribution of dark matter is determined by the cosmic web. The cosmic web is the skeleton upon which the entire visible universe is constructed, the framework that organizes everything from the largest clusters to the smallest satellite galaxies. To understand the cosmos is to understand this web, and yet, For all our understanding, fundamental mysteries remain. We know that the cosmic web exists. We can map it, simulate it, trace its evolution forward and backward in time. We understand the physics that shapes it: gravity, expansion, dark matter, dark energy. We can predict its future with reasonable confidence, watching in our simulations as it thins and dissolves across hundreds of billions of years. But we do not fully understand why it takes the precise form it does. The statistical properties of the cosmic web, the typical length of filaments, the typical size of voids, the characteristic mass of clusters, are set by parameters whose values we can measure but cannot explain. Why is the density of dark matter what it is and not some other value? Why did inflation generate fluctuations with the particular spectrum we observe? Why do the fundamental constants of physics take the values that permit a cosmic web to form at all? These questions push beyond astronomy into philosophy, into the deep puzzles of why the universe has the properties it does rather than some other properties. The cosmic web we observe is consistent with our theories, but those theories do not uniquely predict this particular web. Other values of the fundamental parameters would produce different webs, or no web at all, or webs with properties so different from ours that no observers would exist to contemplate them. The cosmic web we have mapped is one possibility among many, a particular realization of physical law that happens to permit our existence, our observation, our wonder at the universe's architecture. This is the context in which the survey's achievements must be understood. The Sloan Digital Sky Survey and its successors have given us not merely a map but a mirror, a reflection of cosmic conditions that made our existence possible. Every filament stretching across the survey data, every void empty of galaxies, every cluster blazing with thousands of members, all of these structures trace back to the primordial fluctuations of the early universe, to the parameters of cosmology, ultimately to the laws of physics themselves. The cosmic web encodes information about the deepest structure of reality, written in a language of positions and velocities and luminosities, readable by those with the instruments and the mathematics to decode it. The map we have made is incomplete. It always will be. The observable universe is finite, bounded by the horizon beyond which light has not had time to reach us. We cannot map what we cannot see. And even within the observable universe, our surveys are limited by technology, by time, by funding, by the fundamental difficulty of measuring faint light from billions of light years away. Every survey is a compromise between depth and breadth, between resolution and coverage, between the ideal map we would like to make and the practical map we can actually achieve. Yet within these limits, the surveys have accomplished something remarkable. They have revealed the universe's large-scale structure with sufficient clarity that we can recognize its organizing principles, trace its evolution, predict its future. The map is incomplete, but it is legible. The cosmic web is no longer a mystery, but a measured phenomenon, as real and as documented as the continents of Earth. The cosmic web stretches across scales that dwarf human comprehension, filaments hundreds of millions of light-years long, voids that could contain entire superclusters with room to spare, a structure so vast that the fastest spacecraft ever built would require more time than the current age of the universe to traverse even its smallest features. And yet this structure, for all its immensity, is not the largest thing we can contemplate. The cosmic web we have mapped occupies only a tiny fraction of the observable universe, which in turn may be only a tiny fraction of the universe as a whole. Beyond our observations, beyond our horizon, the web presumably continues, filament after filament, void after void, cluster after cluster, stretching toward an infinity we can imagine but never reach. The mind recoils from infinity. It is perhaps the one concept that human cognition genuinely cannot grasp, not merely in the way that large numbers are difficult to visualize, but in a more fundamental sense. We can say the word, we can write the symbol, we can manipulate infinity in mathematical equations with perfect rigor, but we cannot truly imagine it, cannot hold it in our thoughts the way we can hold the image of a tree or the memory of a face. Infinity is not a number, but an absence of limit, and our minds, evolved to navigate finite environments with finite resources and finite time, have no mental category for the unlimited. And yet here we are, contemplating a structure that may be infinite, that stretches beyond every horizon we can define, that continues past every boundary we can imagine. The cosmic web we have mapped is like a single page torn from a book of infinite length. We can read that page, we can analyse its text, admire its calligraphy, study the quality of its paper, but we cannot see the pages that precede it or follow it. We cannot know whether our page is near the beginning or somewhere in the endless middle. We cannot even be certain that the metaphor of a book applies, that the pages beyond our view resemble the one we hold. This is the ultimate horizon of cosmological knowledge, not the edge of our technology, which will continue to improve, not the edge of our mathematics, which may yet produce deeper theories, but the edge of observability itself, the boundary imposed by the finite speed of light and the finite age of the universe. Light that left regions beyond our horizon has not had time to reach us. Light from those regions never will reach us, because the expansion of space carries those regions away faster than photons can traverse the growing distance. The observable universe is a sphere centred on Earth, centred on any observer anywhere, beyond which lies the unknowable. The cosmic web continues beyond that sphere. The laws of physics do not change at the horizon. The same gravitational forces that sculpted the filaments we can see presumably sculpt filaments we cannot see. The same dark matter that anchors our observed clusters presumably anchors clusters beyond observation. The universe is not aware of our limitations. It does not arrange itself according to what we can measure. It simply is, in all directions, at all distances, indifferent to the boundaries our light-speed prison imposes. Some cosmologists estimate that the unobservable universe may be vastly larger than the observable portion. If the universe underwent sufficient inflation in its earliest moments, the true cosmos could exceed what we can see by factors beyond meaningful expression. The observable universe might be to the full universe what a single atom is to the Earth, or what a single photon is to all the light ever emitted by all the stars that ever burned. These estimates are necessarily speculative. By definition, we cannot measure what we cannot observe, but they rest on reasonable extrapolations from the physics of inflation, and they suggest that our cosmic web, vast as it is, may be the smallest of samples, the narrowest of glimpses. This thought, once fully absorbed, transforms the nature of our achievement. The surveys we have built, the telescopes we have trained on the sky, the petabytes of data we have collected and analysed, all of this magnificent effort has revealed a fragment, a genuine fragment, a true piece of the whole, but a fragment nonetheless. We have done what observers in our position can do. We have mapped our cosmic neighbourhood. We have discerned the patterns that govern structure formation. We have confirmed that the laws of physics apply consistently across billions of light years and billions of years. This is not nothing. This is in fact everything we could have hoped for, but it is not everything. It is not the complete picture. The complete picture may be forever beyond our reach, not because our technology is inadequate, but because the universe is structured such that complete pictures cannot exist, such that every observer, everywhere, is imprisoned within a horizon of their own making. The cosmic web we have mapped is our horizon made visible. Every filament we have traced terminates not because the web ends, but because our ability to see it ends. Every void we have measured has edges that are artifacts of observation, places where our surveys grew too shallow to detect the faint galaxies that surely populate the darkness. The structure fades into uncertainty at every boundary, not because the universe fades, but because our knowledge fades, because the photons grow too few, the distances too great, the signals too weak against the noise. And within this mapped fragment, within this horizon that bounds our vision, what have we found? We have found that the universe is not random. The positions of galaxies are not scattered like sand thrown on a floor. They are arranged. They form patterns. The patterns are not simple, not crystals or grids or any of the regular geometries that human architects prefer, but they are patterns nonetheless, structures with statistical regularity, with predictable properties, with measurable characteristics. The cosmic web is a pattern, a three-dimensional network that repeats itself in a statistical sense across the observable universe. Wherever we look, at whatever distance, we find the same types of structures, filaments, walls, clusters, voids, arranged according to the same underlying principles. This uniformity is itself a discovery of the first importance. The universe did not have to be uniform. There is no logical necessity that the laws of physics should be the same everywhere, that the initial conditions of the cosmos should be statistically homogeneous, that structures billions of light-years apart should resemble each other in any systematic way. These are facts about our universe, not logical truths about all possible universes. The cosmic web could have been chaotic, irregular, unpredictable. It could have varied wildly from place to place, with different types of structures in different regions with no underlying pattern that surveys could detect. Instead, the web is coherent. The web makes sense. The web can be described by equations, predicted by simulations, understood by minds that evolved on a tiny planet orbiting an unremarkable star in a typical filament. This coherence is the foundation of cosmology as a science. If the universe were not uniform, cosmology would be impossible. There would be no general laws to discover, only local descriptions of local phenomena. Every region of space would require its own physics, its own history, its own explanation. Science, which depends on the repeatability of phenomena and the generality of laws, could not function in such a cosmos. The fact that science works, that we can make predictions about distant galaxies based on observations of nearby ones, that simulations in supercomputers can reproduce structures we actually observe, all of this testifies to the universe's coherence, to the applicability of general principles across cosmic distances. The cosmic web is evidence for this coherence. It is the same web everywhere we look. The filaments in the northern galactic hemisphere resemble the filaments in the southern hemisphere. The voids at low redshift follow the same statistics as the voids at high redshift, once we account for cosmic evolution. The clusters that form at the nodes obey the same mass functions, the same scaling relations, the same concentration parameters wherever we find them. This uniformity is not perfect. There are cosmic variations, regional differences, statistical fluctuations, but it is real, robust, demonstrable. The universe is comprehensible because it is uniform, and the cosmic web is the largest scale evidence for that uniformity. What does it mean to understand such a structure? Understanding, in the scientific sense, means being able to predict. We understand the cosmic web when we can write down equations that describe its properties, run simulations that reproduce its appearance, make forecasts about what future surveys will discover. By this criterion, we understand the cosmic web remarkably well. The lambda CDM model, for all its mysterious components, for all its unnamed dark matter and unexplained dark energy, makes accurate predictions. It tells us how many galaxy clusters of a given mass should exist. It tells us the typical spacing between filaments. It tells us how the web should have evolved from the early universe to the present. And the surveys confirm these predictions, measurement after measurement, paper after paper, decade after decade. But understanding has another sense, a deeper sense that science approaches but cannot fully satisfy. In this sense, understanding means knowing why something is the way it is, grasping its necessity, seeing how it follows from first principles. And in this sense, we do not fully understand the cosmic web. We know that it follows from gravitation and initial conditions. We know that dark matter dominates its formation. We know that the fluctuations from the early universe provided the seeds. But we do not know why dark matter exists, or why it has the properties it does. We do not know why the early universe fluctuated in the particular way it did. We do not know why the laws of physics are what they are, or why the constants have the values they have, or why there is something rather than nothing. These are not scientific questions in the ordinary sense. They may not have scientific answers at all, but they lurk beneath the surface of every cosmological discovery, reminding us that our understanding, however impressive, rests on foundations we cannot fully examine. The cosmic web in this light is both a triumph and a mystery. A triumph because we have mapped it, measured it, modelled it, understood it in the predictive sense. A mystery because its deepest foundations remain obscure, because the questions we cannot answer are more fundamental than the questions we can. The surveys have shown us what the universe looks like at the larger scales. They have not told us why it looks this way rather than some other way. They have not explained why anything exists to look at all. These mysteries do not diminish the achievement. If anything, they enhance it. The cosmic web is more wondrous, not less, because it points toward questions we cannot yet answer. A universe that could be fully explained, fully understood, fully reduced to principles we already grasp. Such a universe would be smaller than the one we inhabit. The real universe, the universe the surveys have revealed, preserves its mysteries even as it yields its measurements. It invites us further in. It promises that there is always more to learn, always deeper structures to discover, always harder questions to pose. And the surveys continue. The Dark Energy Spectroscopic Instrument is taking data tonight as you hear these words. Its fibres are locked onto distant galaxies. Its spectrographs are spreading their light into rainbows of emission lines. Its computers are recording redshifts that will refine our cosmic map. The Vera C. Rubin Observatory will begin operations soon, its 8-metre mirror gathering photons from billions of sources, building a census of the sky that will dwarf everything that came before. The Euclid Space Telescope is orbiting the Earth, mapping the geometry of the universe with precision impossible from beneath the atmosphere. The Square Kilometre Array is under construction, its thousands of antennas preparing to detect the radio whispers of hydrogen gas throughout cosmic history. Each of these instruments will add to our map. Each will sharpen our view of the web. Each will raise new questions even as it answers old ones. The project of mapping the universe has no natural endpoint. There is always more sky to cover, always deeper to look, always finer detail to resolve. The cosmic web we know today will be superseded by a more detailed web tomorrow, which will be superseded in turn by the web of next decade, next century, perhaps next millennium. The map grows ever larger, ever more accurate, ever more complete, and always, at every stage, surrounded by an ocean of the unmapped, the unobserved, the unknown. This is not a failure of the enterprise, it is its nature. Science does not reach final truths and stop. Science reaches provisional truths and continues, refining, extending, correcting, forever approaching a completeness it can never actually attain. The cosmic web will never be fully mapped. The universe is too large and we are too small, and the horizon that bounds our view will never recede. But within our horizon, within the sphere of observability that contains everything we can ever know directly, we have accomplished something astonishing. We have discerned the architecture, we have seen the pattern, we have understood in the predictive sense how the universe organizes itself at the larger scales, and in seeing this we have learned something about ourselves. The cosmic web is not made for us. It has no purpose, no intention, no awareness of the minds that study it. The filaments would stretch across the darkness whether or not any observer existed to trace them. The voids would yawn between clusters whether or not any telescope ever measured their extent. The web is simply there, a consequence of physics, a structure that follows inevitably from the initial conditions of the universe and the laws that govern matter's behaviour. It does not need us. It does not know us. It would continue, unchanging in its statistical properties, if humanity and all other observers vanished from the cosmos without a trace. And yet we are here. We exist. We observe. Somehow in this vast structure that does not need us, minds have emerged that can contemplate it. Somehow, on a rocky planet orbiting an ordinary star in a typical filament at the outskirts of a modest galaxy cluster, there arose beings capable of building telescopes and training them on the sky, of writing mathematics that describes the universe's large-scale structure, of feeling wonder at the immensity of what they have discovered. This is not something the universe had to produce. Observers are not a necessary consequence of cosmology. They are an accident, a contingency, a local phenomenon that could easily not have occurred. The cosmic web we have mapped includes, somewhere within its countless filaments, the conditions that produced us. The heavy elements forged in stellar cores, the planetary systems assembled from circumstellar disks, the warm, wet worlds where chemistry became biology, and biology became minds. We are part of this structure even as we study it. We are not outside observers looking at a universe separate from ourselves. We are embedded in the web, made of its matter, shaped by its forces, bound by its laws. This is perhaps the deepest truth the surveys reveal. Not just that the universe is large and structured and comprehensible, though all of that is true, but that we who comprehend it are part of it. The cosmic web is not other. It is us, extended across billions of light years, arranged into a pattern we can finally see. The surveys have shown us our context. For most of human history, we did not know this context existed. We knew the earth, and we knew the sky, and we imagined various relationships between them. The dome of heaven, the celestial spheres, the infinite abyss of uncharted stars. But we did not know the web. We did not know the filaments and voids, the clusters and walls, the three-dimensional structure that organizes the visible universe into a coherent architecture. This knowledge is new. It belongs to our generation. to the generation that built these surveys and analysed their data and drew these maps. Standing here, knowing what we know, we occupy a unique moment in cosmic history. The universe is old enough that structure has formed, that galaxies have assembled into clusters, that filaments have stretched across the voids. But the universe is young enough that the web is still visible, that the expansion has not yet carried distant structures beyond our horizon, that we can still detect the ancient light that carries information about the cosmos's youth. This window will not last forever. Eventually the expansion will accelerate beyond a critical threshold. Distant galaxies will recede past the horizon. The cosmic web, from the perspective of future observers in our region of space, will appear to dissolve as more and more of it becomes unobservable. Our descendants, millions or billions of years hence, may know less about the large-scale universe than we do now, not because they are less capable, but because the universe will have hidden itself from them, withdrawn behind horizons that even light cannot cross. We are fortunate to live in an era when the cosmic web is visible. We are fortunate that our technology has reached the point where we can map it. We are fortunate that the laws of physics permit such mapping at all, that the universe did not arrange itself in ways that would obscure its structure or prevent its observation. This fortune is not guaranteed. It is a gift of cosmic circumstance, a consequence of where and when we happen to exist. Other times, other places, other observers might see less, or see differently, or see nothing at all. We see the web. We have made the map. This is our achievement, our generation's contribution to the long project of human understanding. The map stretches before us now, complete in its incompleteness, finished in its unfinishedness. It shows us a universe of filaments and voids, of clusters blazing with thousands of galaxies and walls stretching for hundreds of millions of light-years. It shows us the observable universe, that fraction of all that exists which light has had time to illuminate for our eyes. It shows us patterns that repeat themselves, structures that follow laws, a cosmos that can be understood even if it cannot be fully explained. And beyond the map, beyond the survey's reach, beyond even the horizon of observability, the universe continues. Filament beyond filament, void beyond void, structure beyond structure, presumably, stretching toward a totality we will never see and can barely imagine. The cosmic web we know is a sample, a fragment, a single movement in a symphony of infinite length. But it is our sample, our fragment, our movement, and it is enough. It is enough to feel wonder, enough to feel smallness and grandeur combined, the strange emotion that comes from knowing your own insignificance within something magnificent. Enough to look up at the night sky and know, not imagine, not believe, but know, that the stars you see are arranged in patterns, that those patterns extend beyond your sight, that the universe has a structure you have helped to reveal. The Sloan Digital Sky Survey began with a telescope on a mountain in New Mexico, pointed at the sky night after night for years. It ended with a map that changed how we understand the cosmos. The cosmic web it revealed was there all along, hidden in the positions of galaxies, encoded in patterns too large for any eye to see. The survey decoded those patterns. It showed us the web, and the web in turn showed us ourselves. Small creatures on a small world in a small corner of a structure so vast that the human mind cannot truly comprehend it. Creatures who, despite their smallness, built instruments to measure the immeasurable, who devised mathematics to describe the indescribable, who looked out at the universe and saw, not chaos, not randomness, not a void without meaning, but a pattern, a web, a structure, something that could be known. The universe is under no obligation to make sense, but it does make sense. The cosmic web is proof of that. A pattern this large, this coherent, this beautiful in its mathematical regularity. Such a pattern did not have to exist. It exists anyway, and we against all odds have lived to see it. Perhaps that is the deepest wonder of all. Not the web itself, though the web is wondrous. Not the surveys, though the surveys are magnificent. But the fact that we are here to see it, that the universe produced somewhere in its endless filaments beings capable of mapping those filaments, that the structure became conscious of itself, in us, in the act of observation and understanding. The cosmic web stretches across the observable universe, hundreds of millions of light years per filament, voids vast enough to contain everything humanity has ever known with room to spare. It is the largest structure we have ever mapped, the deepest pattern we have ever perceived. And now you have seen it. Now you know what the universe looks like at the largest scales our instruments can reveal. It looks like a web. It looks like neurons. It looks like silk threads spun across darkness. It looks like something built, something designed, though it was built only by gravity and designed only by the laws of physics. It looks, in the end, like the universe, vast beyond comprehension, patterned beyond expectation, beautiful beyond any requirement that beauty should exist. The map is made, the web is known, and the universe, indifferent and magnificent, continues on its way, filament after filament, void after void, stretching toward an infinity we will spend forever trying to imagine.